PHY2SUDOE final conference. Today we have the second day of the presentations, and it's all in English. It was in the program that yesterday we had translation, but today no. Today everyone has to speak in English. So we have three sections today. We have first the presentations of the PHY2SUDOE project. So that will be a summary of these 3 years of work. And we will be making short presentations about the results of the project and the working groups. After that, we invited 3 other European projects working in related fields. So we will have the pleasure to hear about 3 projects that are dealing with the same problem in a different way. And finally, we wanted to invite also the academia and the students and postdocs to show the recent work. So we gave the opportunity to show posters. They are displayed in the coffee room. And from those 13 posters, we selected 6 that will be presented orally. So I'll just give the word to Carlos. Carlos is the research director of NICER. He's a biologist. He did his thesis in College London, and he's been working in soil microbiology for a while, and he's the leader of the soil microbiology research group, or he was until this recent position, and he also was the lead of the natural resources department for many years at NICER. Thank you, Carlos.
Thank you so much, Juan. See if I don't have an accident here. My presentation is over there. Okay, thank you for coming. My name is Carlos, and I was supposed to give a brief introduction to the PHY2SUDOE project, but since I have seen in the program that there are so many good talks on PHY2SUDOE, I have decided just to very briefly describe some of the things that I have learned during the development of the project. Well, in any case, this Phyto adventure started in 2016. In the first PHY2SUDOE project that was coordinated by our beloved and always remember Petra Kid. And at that time, now I'm at the end of the second PHY2SUDOE project, I do realize that the foundations of good phytomanagement were already there in the first PHY2SUDOE proposal. Now I'm going to describe some of the things that I learned from my PHY2SUDOE friends in the first PHY2SUDOE project. From Petra's group and from Michelle, from the beginning, I did learn the meaning of phytomanagement. At that time, I have to admit that I didn't know the term phytomanagement. I was working in phytoremediation, and I was focusing all my attention in the reduction of contaminant concentrations. But Michelle and Petra told me, at the same time, Carlos, we can generate valuable products and ecosystem services. And at that time, I thought, and well, I still think, it is a very good idea. Then Chema, who is the person who introduced me to the phytoremediation field 20 years ago, 25 years ago, I think, told me about the criticality of a complete characterization of the site. He always insists on going to the field, going to the site, analyze every single plant species, and of course, all the soil properties, the soil contaminants, and that's also essential. It is critical. From Michel Mensch, I did learn the criticality, the importance of having a good conceptual model. He always told me, Carlos, we need a good conceptual model, and a model that includes all the relevant pollutant linkages, and he cannot be more right. It is essential in any of these remediation projects. From Paula and her team in Oporto, I did learn about the existence of plant growth promoting bacteria. Of course, I knew about mycorrhiza, but at that time, I didn't know that we could use endophytes and we could use rhizosphere bacteria to enhance plant growth under phytomanagement. So they were already talking about symbiosis. From Chema, I also learned that we need to protect plants growing in polluted sites as unique biodiversity. The first time he told me so, I thought, this is a strange conservation in contaminated sites. So I think this is strange, but then he brought to my attention a very relevant paper on this question. In any case, with all our backpacks full of ideas and new concepts from the first PHY2SUDOE project, we moved to the second PHY2SUDOE project that has been fantastically coordinated by Lure Pelde. And in this second PHY2SUDOE project, we have not only expanded the network of sites under phyto management. Following Chema's advice, we have also promoted the conservation of biodiversity. Here you have a list of the different partners of the PHY2SUDOE project. Since you are going to meet them in the next few talks, I'm not going to describe them in detail, just to tell you that I do believe it has been a fantastic consortium. Then from Manu, in the second PHY2SUDOE project, I have learned that it is not about selecting the best technique, the best remediation technique. It is about making a puzzle with the different techniques, and physicochemical, biological, bioremediation, phytoremediation, vermi-remediation, but it is a dynamic puzzle. It is not only a puzzle, it is dynamic. It must change over time. Then I have learned, the importance of promoting interactions and interconnectedness between the different taxonomic groups, between the plants that we use for phytoremediation or phytomanagement, their microbiota, soil bacteria, fungi, earthworms, and so on. It is certainly about interaction, and it is about promoting symbiosis. Then, one thing that I have also realized is apparently there is never enough money or interest in repairing the environment for the sake of the environment. So we must link the concept of remediation to the concept of human health. But not only in general terms, like saying, okay, if we grow plants, we are going to have more oxygen and a nicer landscape. No. We really need to attract the attention of the public. And one possibility is to talk about human pathogens. We are all afraid of pathogens. And we know that many polluted sites are located in urban and peri-urban areas, And we also know now in the last few years that when we introduce trees in the urban environment, the abundance of pathogenic bacteria decreases. But it's not only human pathogens, it's also the microbiota. Now we all know about the importance of microbiota for our health. And many people are talking about restoring ecosystems in order to supply humans with the right dose of microorganisms that can improve our health. Of course, I'm talking about microbiome-inspired green infrastructure. And some people are even talking about the link between the microbiota and social equity. Many polluted sites, as I have told you, are located in peri-urban degraded areas, sometimes in poor neighborhoods, without a nice green infrastructure. So phytomanagement is a great opportunity to introduce green infrastructure in degraded areas and to provide people with a healthy microbiota. Well, above all, I have learned the importance of thinking in terms of networks, patterns, processes, flows of matter, of energy, of information, and context, and that is why we must always incorporate the paradigm of adaptive management. And in our sites under phytomanagement, we must build resistance and resilience. From the point of view of processes and context, we must remember that all living creatures, including the ones that we use for phytomanagement, are extensions of the Earth's spheres, and climate change is altering all these spheres. Also, we must look at organisms not as fixed structures. We must look at organisms as processes, as patterns of activity. And concerning the flows of matter, remember, just an example, the element tone is a reliable indicator of the plant's functional traits and their ecological strategies. So we can use it. It is a good predictor of how ecosystems work. And when we are doing phytomanagement, we are dealing with ecosystems. And of course, living organisms persist by virtue of complex interactions among many components organized into dynamic, environment-responsive networks that span multiple scales and dimensions. But it is not only about network topology, it is also about network dynamics. Also from my friends, from my PHY2SUDOE friends, I have learned this kind of web of life philosophical approach to the remediation of contaminated sites. When we go to a contaminated site, we must be thinking in terms of depositing a web of life on them, about transform them into places conducive to life, into places where nature connectedness can provide eudaimonia to humans. In other words, I'm talking to transform them from dysbiosis to eubiosis, because it is certainly all about life. And in this last slide, I want just to present a dream. My dream that young people will continue with this adventure. And just to provoke the young people in the audience, of course, in a good way, you know, just in case one of them takes up the challenge. You know, here I have included here a tentative title for maybe a project proposal. Management of evolving, I underline evolving, it is a key word here. Biological alliances, for me it is a much better term, biological alliances, than symbiosis. And networks in polluted sites for human health and well-being, and the promotion of the life's ecological web. In the 15th century, Leonardo da Vinci said, we know more about the movement of celestial bodies than about the soil underfoot. And unfortunately, that statement is still true today. So I do encourage the young people here to enter the remediation, the biological remediation field, because so much remains to be done. Thank you so much for your attention, and a special thanks to my PHY2SUDOE friends for being such a fantastic consortium. Thank you so much. Now I think Juan is going to be the moderator. Juan? Yes. Yeah, okay.
Thank you. Thank you, Carlos, for the overview and also for bringing those challenges to the room. So now we move to the next talk, which will be given by Ángeles Prieto. She's a tenure scientist at the Misión Biológica de Galicia of the CSIC in Santiago de Compostela, and her experiences is focused on the study of biochemical and microbiological biological properties of soil degraded by forest fires, agricultural practices, or contamination.
So thank you, good morning to everybody. So as Carlos has introduced, we've been working for 3 years now in a project that has different work packages, different objectives. One of them was based on monitoring sites that we had already established in a previous PHY2SUDOE project. And then another work package was dedicated to implementing new phytomanaged sites. In my case, I'm going to explain you a bit some of the results we obtained, or some of the conclusions we obtained from the sites that were located in Galicia, on the northwest of Spain. From the previous project, we had a site in Pedrafita, which is a mine tailing. It was a lead and zinc mine. And we had another site in Douro, close to Santiago de Compostela, which was a copper mine. And then during this second PHY2SUDOE project, we established a new site also close to Santiago, and in this case it's a serpentine quarry. It's a kind of rock which is very poor in silicon and rich in elements like nickel, chromium, and cobalt. Regarding the Pedrafita mine, as I said, it was dedicated to the separation of lead and zinc. And the mine is quite big. It's about 30 areas, the tailing. The system was separation by flotation. And the main contaminants there are lead, zinc, but also cadmium. So we work in a small area of about 4,000 square meters in the mine tailing. In this area, we established three big blocks, and in two of them, we did not apply any organic amendment, while in the third one, we applied compost from municipal wastes. We worked with Salis smithdiana, which was planted in monocropping or intercropped with alnus. In the two blocks that we did not apply amendment, we just tested the growth of Salis in monocropping or co-cropping, and we also tested the application of some NPK fertilization. This was established in 2011, and then in 2017, in the second block, we tested the inoculation with plant growth promoting bacteria. Finally, in the third block, where we apply compost, we also tested the growth and compared with the non-amended area, the growth of salix alone or intercropped with alnus. Here are some pictures of the site. The first one is how the place looked when we went there. As you see, it was almost bare, almost free of vegetation, so we did some work with heavy machinery and so on. And we also made a very deep sampling of the site and analysis of the site before initiating the experiment. And the last picture is the appearance of the salis after 2 years of growth in this site. And these are pictures we took last time we went there for sampling. In general, the survival of salix was about 50%, and this was independent of the treatment applied. But in the site we began in 2017, the survival was much better. In this site that we established in 2017, we also observed things like we were measuring the trees, and for example, the slide shows the tree height, and we could observe that in places where we didn't apply the bioinocula, in general, the trees were shorter than when we applied certain inocula, as for example, Massilia P87 or even Bacillus ski, which is the pink bars. The variability is quite high, but anyway, we think that the bacteria we applied, they helped the system to work. Other aspect we analyzed in this site was we were worried about the availability of the metals, because it's not only a question of the total amount of contaminant, but also the availability of this contaminant. And we analyzed this availability with different extractants like ammonium nitrate or EDTA. In the area where we didn't apply the amendment, we saw that the trees contribute to slightly increase the availability of these contaminants. Although with time, this availability tend to decrease. The bars I'm showing there are the values we obtained 6, 7, and 10 years after initiating the phytomanagement. As you see, in many cases, the availability was decreasing with the time. And we also observed that this was mainly for the more available fraction of the contaminants. But when you extract the contaminants with EDTA, which offers a fraction not so readily available, the influence of the trees was not so pronounced or even was not significant. In any case, the amendment helped us to control the availability or even to decrease the availability in comparison with a non-treated area. We also monitored several properties. I'm showing here just few, which are quite important for the development of the vegetation. For example, for pH, with NPK, we saw a decrease in pH, which was probably related to the increase in metal availability. And we also follow the phosphorus concentration, which was improved with the organic amendment and of course with the NPK fertilization. In general, the phosphorus availability tends to decrease, so for the moment we didn't detect a big problem of fertility, but this could be something we could check in the future. Regarding the organic matter, of course, as expected, we found an increase in organic matter in the area where we applied the compost. And we also observed that in areas where we planted the trees, the organic matter was maintained during all the period of study, while in the area where we don't have trees, the organic matter tends to decrease. Of course, also where we didn't apply the amendment, we see that the organic matter tend to increase because of the presence of the trees and all the carbon fixed by the trees. This also reflects on some properties which are quite related with organic matter, such as cation exchange capacity or water retention, which are also very important for maintaining the vegetation there and for the fertility of the site. In general, again, the place where we apply compost was responding better and was offering better results. If we look at the biological activity in the soil, which is really working there, then we also see a positive effect of the organic matter addition. It seems is essential. We always find higher activity in the area where we apply the compost. And we also analyze the diversity, the functional diversity of the bacterial communities in this soil. In general, the higher values were also obtained in places where we have trees or where we have trees in combination with the amendment. NPK in some cases is also increasing, like for example, beta-glucoxidase. The second site we worked at is PHY2SUDOE, which is a copper mine. The problem there is the concentration of copper, but also the stream acidity, because the pH of the substrate is 3 or even below 3 in some areas. This is due to the minerals present there and the oxidation of the sulfides, which generate a high amount of sulfuric acid or of acid. We worked in an area of about 2,000 square meters in this huge tailing of the mine. As in the case of Pedrafita, we also had 3 big blocks, and here we had to apply amendments everywhere, otherwise the growth was impossible, the space was completely bare. So we applied compost and 2 different technosols, one enriched in iron, and the second one enriched in aluminium. The plant species we worked were Salis, Populus, and Agrostis. These are pictures of the site when we began the experiments. As you see, it was absolutely bare and it was very compact, so we had to work with heavy machinery to move the site, to characterize adequately all the area with a very deep sampling, and then we apply the compost and the technosols. These are pictures we took during PHY2SUDOE, and as you see, the trees, we had a quite high mortality in many of the plots, but the trees that survived were healthy, in good condition, and the site, the appearance of the site is of course much better than initially. As in the case of Pedrafita, we were worried about the copper availability, and we analyzed with different extractants. These are again the values obtained 6, 7, and 10 years after initiating the phytomanagement there. And we see that all the treatments contribute to strongly reduce the copper availability, which was up to 85% in the case of ammonium nitrate, or up more than 700 in the case of EDTA, and all of them, all of the amendments contributed to drastically decrease the copper availability, and this was maintained along the years. Now the last bar corresponds to 10 years after phytomanagement. The more labile fraction tends to increase, but when we analyze the EDTA copper, we see that everything is still quite good. And we also analyze the aluminium availability, because in this such extreme environment, the aluminium is very soluble and it induces a strong phytotoxicity. as in the case of copper, the aluminum availability is well controlled in all the phytomanaged areas, especially where we have trees. And this is to show you that because this project started in PHY2SUDOE, but we had already some experiences from before, from a previous project. We have, in some cases, data for all these years, 1, 2, 3, 6, 7, and 10 years. And these are some of the properties we analyzed there, and we see that the management we did was maintained along the time, which I think are good news for the phytomanager people. For example, we see that the pH is controlled from the very extreme low values we had in the site, like pH 3, almost absolute absence of organic matter, or extremely low availability of phosphorus. With all the treatments, we improved that. In the case, for example, of phosphorus, it tends, as in the case of Pedrafita, to decrease the phosphorus fertility, and this might be something we have to care about. But for example, for organic matter, we observe that is maintained for a long time, and even in the case of compost, as you see, especially in places where we planted trees, there is an increase with time. So the system is cycling and is establishing stable cycles and is self-sustainable somehow. In total, we also analyze some physical properties, such as, for example, density or porosity, which increased with all the treatments applied, and also the water retention. In the case of the water retention, are data from the last sampling. And in this case, we observe that the trees have an additional benefit. A part of the amendment we applied, the trees had a benefit on all these properties, like the water retention or the stable aggregates. In the case of the water retention, we analyze both the gravitational water retention and capillary water retention, and the effect of trees is observed mainly in capillary water retention. And regarding the biological properties, also we have an improvement of the properties in comparison with the non-treated area. And in some cases, we observe an effect of the trees applied there. The result is better than with agrostis. The functional diversity also tended to be higher in areas with plants. And finally, we have the Bandeira site, which was established during PHY2SUDOE. In this case, as I said, is an ultramafic area. These rocks have very low silicon content and are naturally rich in nickel, chromium, and cobalt. The quarry is still active. The big area, they are still extracting sand, gravel, and ballast and material for public work. And we worked in an area that is not active in the moment, and we have a fenced area of about 2,000 square meters. In this case, the approach we applied is nickel phytomining. This is a technique that consists in growing plants that are able to hyperaccumulate certain elements. In this case, we worked with nickel hyperaccumulators. These plants can uptake from the substrate the trace elements and accumulate them in the shoots. In the case of B. marginata, Bormolia marginata, which is one of the species we work with, in agricultural soils, we reached values of about 0.3, between 0.3 and 1.5% of nickel in the shoots, which is quite high. So the phytomining is growing those hyperaccumulators, and then we harvest the biomass, we bar the biomass, and you can extract the elements from these ashes. This is especially useful in case of elements with a high value in the market, like as is the case of nickel. We work it in small plots of 20 by 20 meters, and with two species. These species are native from Greece. It's Bormolia marginata and Bormolia tymphaea. And as the place was very arid, we had to apply compost, and we tested 3 different doses. These are pictures of the site where we installed a watering system. We used seedlings that we produce in the greenhouse, and as you see in this case, everything was quite manual, so we did all the work by ourselves, and also some pictures of the plants already growing there. We were quite happy with the survival. In general, was good, both in 2.5 and 5% compost. We had to forget about 10% because it was too high, and then the other plants growing on these very heavily amended areas overgrow the hyperaccumulators. So this was not good for our experiment. For the moment, we have just 1 harvest. We plan to harvest now, probably after Easter, because it's the time for harvesting these plants. You can see that, of course, in the places where we apply compost, we have an increase in carbon, and we have a decrease in metal, which is a kind of dilution. As we added additional material, then the total content is lower, but we have an increase in availability. In this case, it's not very worrying because the increase is not very high, and this is good for our hyperaccumulators, that they need some availability of nickel to be there in the soil for being uptaken. If there was no nickel available, they cannot uptake, of course, the nickel. The first harvest, as I said, we had better biomass results with Borboniera marginata, much better results, and more or less the amount was the same in 2.5 and 5% plots. But when we look at the nickel yield, which is the total amount of nickel we could get per hectare, this depends, of course, on the biomass, but also on the concentration of nickel in the plant tissues. We got better results with a 2.5% compost amendment. We have now to follow the re-sprout of plants, because ideally we should have some re-sprout and avoid planting every year the plants. This would be the perfect solution. So as summary, some ideas that we have found that organic amendments are very important for managing these sites, especially in case of low fertility, acidity, or aridity. In Pedra we succeed in growing the plants without amendment, but in some cases this is absolutely essential. The organic amendments ameliorated the soil properties, and this was maintained for a long time. Now we have data from 10 years. So they act as a kind of a starter for a successful management. And then we think that it will be important to test from time to time the availability of the most toxic elements, such as, for example, cadmium in the case of the Pedrafita mine. And in the case of the phytomining trial, it could be a complementary alternative to phytomanage those sites. Also, and despite the high value of nickel in market, at this moment we cannot say that it's economically profitable for the owners of the quarries. So with this, just some names of the people that worked there. This during the PHY2SUDOE project. For the PHY2SUDOE, the list would be bigger. Many students, many people helped us to establish and maintain these sites. And that's all from me. If you have any questions, thank you. Are there questions? I think our partners, they already knew big part of the story. Thank you. Yeah.
I saw that you use 2 different Salix species. One was Viminalis and the other Smithiana.
Yeah.
And in different sites. That was some purpose based on research, or
we really tested more than this species, because in Pedrafita I think we tested 3 more species, another hybrid which was Tora, and another hybrid of Capre, I think, and in Touro also we tested other species. But finally, the ones that show better survival and were able to adapt were those two. In fact, the Viminalis is from the surroundings of the mine. We tried to introduce other species, but the more successful one was the one from the site, which is a bit linked to what Elena is going to present us about the work package of PHY2SUDOE, about preserving and caring of the biodiversity of these degraded sites that can provide us useful tools for recovering the areas.
thank you.
Yeah.
There's a general question about phytomining. Do you know if it's been successful commercially in some parts? Because I was following phytomining at the beginning as a great idea. Cheney and all that group with phytomining. But do you know if it's been commercially successful?
I know that in Albania and Greece they are establishing experiments, and in Albania they are using a different species, which is Odontorrhena muralis, that we cannot, because it's invasive. It provoked problems of invasion in the States. The group of Chani, they have problems in Oregon with this plant, and also in Greece. And there is a company, Econic, which was derived from a life project, and they are working with Borboyeratin faya in Greece, and they are very happy with the results. Well, in some areas in Albania, they got up to 300 kilos per hectare. And then, of course, then you have to make numbers, because it's not mechanized for the moment. So, but anyway, as Europe is so deficient in this kind of elements, which are so important for all the technological tools, it can be an alternative. But for agricultural soils, I don't think for places like a quarry, they can be very profitable. Okay.
Thank you, Angeles. So now we move to the next speaker. Is Michel Mensch from France. He works in the INRAE, the National Institute of Agricultural Research of France. He started working in the 80s with trace elements in soil play system, obtaining his PhD degree in the National Polytechnic Institute of Lorraine. And since then, he has published 175 peer-reviewed papers in scientific journals. Since 1992, he's working in the phytoremediation and phytomanagement of trace elements and DL-drain contaminated soils. Michel?
Muchísimas gracias, Juan. You know, it's a 3-language project, so buenos dias, todos socios, bonjour à tous, and bom dia, Portuguese people. Let's go. Yeah, first of all, I would like to remember a little bit the definition of phytomanagement, because it could be not clear. Carlos introduced a little bit in a slide. It's a long-term combination of profitable crop production or other greenland use with gentle remediation option, leading gradually to the reduction of pollutant linkage due to contaminant excess and the remediation of ecological function underlying ecosystem service. What is important, it is not the total soil contaminant. The purpose is not to decontaminate, but it is to address the bioavailable contaminant and especially to reduce the supply of contaminant to the soil solution or any exposure pathway, and also to avoid excessive exposure of the living organism. And sometimes you can even change the biological receptor to have much more interesting biological receptor to avoid such exposure pathway. So this is the target, the exposure pathway and the bioavailable contaminant. How we can do that? It's a former slide of Petra adapted to this project. It is by targeting the soil functionality through plant nutrient, organic matter, physical, chemical, soil property, pollutant linkage, microbial diversity, and so on, then you can modify the ecosystem and remediate the ecosystem service and promote them. The purpose is not to go back to reference value. Most of the time it is to create a new ecosystem and to put, use the plant community, the microbes, the mesofauna, to put the ecosystem on a new trajectory, especially according to the future land use. So it is the reverse compared to phytoremediation concept. We start from the future land use, how we can use a different tool to put the ecosystem on a trajectory to reach this land use. Now, I remember that when you have like a poplar, an oak, a salix, what you want, it's not a plant. It's an ecosystem, as mentioned by Carlos. You have, at the same time, the associate microbes, especially the endophytes, the mycorrhizas. You have the mesofauna associated with the organic matter, especially if it is driving by the litter. You have all the microbes associated with the rhizosphere. And at the same time that you can, for example, uptake and biotransform the organics in the plant, you have also some phytostabilization like lead or copper in the root. You can have also uptake of cadmium and zinc in the case of poplar, and storage apart. You have a storage in the root, but also storage in the leaf or the bark of very young branches. You may have some volatilization in the case of selenium. You are stimulating through the rhizodeposition all the bacteria and sometimes the fungi also associated with the rhizosphere, and you stimulate also the mesofauna, all the animals that are really, really important for the cycling of nitrogen, phosphorus, carbon, and blah, 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 and especially also the contaminant. So keep in mind that when you have a plant, it's an ecosystem and you are using different actors at the same time. Now, I will talk, we have different sites. The former one in PHY2SUDOE site, Saint-Médard and Chabon, but today I will talk about Durando, Les Avinières, and Borde, because we don't have time to address all the sites, but we have all these sites in red, outlined in red, in France at the moment, running in the framework of the PHY2SUDOE project. Now, what is Born? Born is a former landfill. The future land use is to create a recreative area, and the macro waste were removed. Here you can see they were polluted the river. Even during the flood, the macro waste were removed and go to the estuary. But they want to change that. So they remove the macro waste. Then they were sieving the small particle and replace the small particle the same place and remove the waste. They implement ryegrass and white clover, and you have here, for example, the composition of the soil and the contaminants. It was mainly contaminated by copper, zinc, a little bit by lead, but we have organics because some industrial companies were also dumping their chemical waste at this site. Fortunately, the pH was 8, and we have a reasonable carbon concentration. So what happened about the strategy? Yes, very important. Amendment, bioaugmentation, so put microbes from different origin, and also try to phytostabilize or rhizodegrade using especially clover, the organics. So this is a view. After 3 years, and it is a view now after 5 years. We collect the picture especially for you in March, and you can see we have a meadow. The trees are not, it's local trees. They're not growing very well, but not due to the contaminant. It's due because the community, especially the city was not taking care of the site, and they were not irrigating the trees during the heat wave of last year. That's the main problem. It's very important. For the first or 2 years, you have to irrigate the trees to pass the summer drought. This is the shoot ionome, so the concentration, for example, in the shoot or in the leaf. This is for the clover, for the white clover and the ryegrass. You have the different metal and metalloid. If you look about this value, it's very, very low. Despite the contamination, it's very low. We don't have, for example, cadmium accumulation. The value for fodder, cadmium in the fodder, it's 2. The maximum permit value, for example, for green forage in France, it is 2. Look at this. It's a logarithmic scale. We are around less than 0.5. It's really remarkable. Even this meadow can be used for rearing area, except one thing, you have to take care that there is no direct soil injection, especially by the keto. But we have just a small square of plot at this 5 plot where we can see some symptoms like a purpling of the bottom of the grass and a change of the grass. It was mainly Eolcus lanatus and not ryegrass. And if we look carefully to what happens at these small plots here, we have too much extractable chromium, and we have an increase of the iron in the shoot due to an antagonism effect. But it is very, very located. But I want to be really pragmatic and give you also some limitation. Due to the spatial variability, we may have some spot with less successful story. But it's not a problem. It's only due to an excess of iron in this case, and it is probably induced by too much chromium, but the chromium was chromium-3. Maybe we may have also some other things here. If you are familiar with copper and zinc, look at this. This is reference value. We are below this reference value. What happened with carbon? We increase the carbon in the soil, and you can see there is a clear sequestration of copper by the organic matter, and we have a decrease of the copper availability, especially because we increase the organic carbon. Now, we can go even further. We have tested the addition, the supply of much more organic matter using compost, and there is 2 effects in this case. You promote the growth of the plant, but you also promote the seed bank, and then you increase the and we increase the functional activity, except at the plot 5, where we have such excess of chromium. We are not reaching at the moment the reference value for an uncontaminated soil, but we are on the way. So we have a good, relatively good recovery of the soil microbial activity. Now, Durando, it's a new site. Again, it's a former battery factory. We have all you want. So we have metal, metalloid, we have pH, we have volatile compound like trichloethylene, we have PCB. Fortunately, the pH is very high. It's around 8. It's a sandy texture. What happened? A large part of the site was capped with concrete. So we removed the concrete, You can see now we create a plot. First of all, we were testing. It's very important. Before to implement any phytomanagement project, you have to test, to characterize the site, to test in plot before to implement, and you need to characterize the different zone of the area. So what we were doing, we were testing different strategy using different plant, especially because we have a lot of nickel. We were testing the metallophyte with Angeles and other colleagues from Santiago, but it does not work very well because in fact the nickel availability was low and the pH was too high, probably. But for poplar, agrostis and other plants, it was working well. So the purpose was to volatilize the trichloroethylene, to phytostabilize copper and lead, to rhizodegrade the PAH, TCE, PCB, so all the organics, and try to also remove some cadmium and zinc using the poplar leaf. So what happened? This is a scheme of the implementation of the plot. We use also compost. We design a strategy using different plant species like vetiver, poplar, miscanthus, ryegrass, alfalfa. I could explain later why we are choosing all these plants. Very important things. We are not using plants from commercial nursery. No, we are using plants because the population coming from contaminated sites, they have endophytes, they have mycorrhiza, they are adapted to contaminants. So when you are implemented some plant species, it's better to use the plant coming from contaminated site. Even the site where you are working, you may have the good adapted population. I can comment later on that. Important point, we have also lysimeter to control the quality of the water leach from the soil with and without amendment. Look, this is very important. You need irrigation at the beginning if you have heat wave like last year to stimulate and to promote the growth of the plant. And you can see here we have the vetiver, here we have the ryegrass and alfalfa. Here you can see some poplar here developing well. These poplar were inoculated with endophyte, especially for the degradation of trichloroethylene. It's coming from the strain selected by Jacob van Groosveld in Ghent, the previous Greenland project. Now, this is the view of the plot after 8 months. So, one key point. When people told you, wow, phytomanagement, it's taking time. No, it's rapid. You can establish rapidly a community. Look about the concentration of the contaminant in the shoot. The metalloids are very, very low. Even we were not extracting cadmium and zinc in poplar because the pH was too much, too high. We have some symptoms here, and it could be a little bit, it was strange, but it could be also some symptom of organics. We were not able to retrieve any trichloroethylene in poplar. Was not expected. We were expected to have trichloroethylene, but this did not happen. We only have such PCB and hydrocarbon, but it was in the green leaf and not in the leaf with some symptom. For the moment, we were comparing the composition, but we have not discovered what is happening really to explain that. It was the only one. It is in the bottom leaf here. If you look about the miscanthus, the vetiver, they don't display any symptoms. And if you look about the concentration of the contaminant in the leaf, finally there is no transfer, very, very low transfer to a potential herbivory. We were managing also the leakage from the lysimeter, and if you look about the concentration, if you are familiar with the concentration in the leakage, it's very, very low. We were even able to decrease, this is without amendment, and this is with amendment, we were able to decrease the trichloroethylene in the leakage. Only things, it is a small increase of nickel here, because we decrease a little bit the pH due to the nitrification of the organic matter that we applied as a compost. But if you look about these concentrations, they are very, very low. And it is even possible to have a small constructed wetland to collect such water and to even clean such water. Now, Les Avenières, it's a former mine. The strategy was to phytostabilize and bio-augment the soil, especially with rhizobium. The main purpose was to avoid the wind erosion, and because we have slope, this is very important to establish banquet. In this case, so the purpose of Fertilinov, PHY2SUDOE, was to select the plant species adapted to have a good vegetation cover and avoid the transfer of the contaminants. We have mainly zinc, cadmium, and lead at this place. This is the strategy. It was to correct the physical chemical property, to show specific population to have a good vegetation cover, and to monitor the plot. The plot were implemented on a large zone in 2022. With here you have the inoculation of the about the symbiotic microbes, and this is a trio just at the beginning. This is a view of the plot along the year. After 1 year and a half, you can see the different covering of the plot, and you have a good vegetation cover, avoiding the erosion and stabilizing the particles of the soil. If you look about the soil property, we have an increase due to the compost and plant. We have an increase of the organic matter. We have an increase of the microbial biomass. We have a diversity. This is the different plant species. And if you look about the plant community that she was establishing, we have one species that is a zinc accumulator. It is Anthelis vulneraria. But the other plant species, they are mainly zinc excluder. And if you look about lead, thallium, cadmium, the concentration in the shoot are very low. So just to remind you, we have other plants in France, especially Marie-Cécile Alfolder is presenting a poster about the phytomanagement of dieldrine, exactly a little bit like the case of Guernica, also in Basque Country. And you can have much more information about to address such organics using reading her poster. Finally, some take-home message. Always there is always a sustainable solution to every case studies. Also, try to zone the site. A site is never homogeneous, so you have to address a strategy according to the different site. The main drivers it is the land value and the present and future land use. That's the main driver. You have to identify local chain for processing the biomass, because remember, one of the purpose it is to process the biomass. Success story, always the key, it is the synergy between scientist, owner, manager, authority, stakeholder, consultant. If you miss one of these actors, you will miss it. That will be not a success story. You start from the pot trial to a field trial, but it's not a so long journey. If you look about people generally, especially the local or national authority, when they are talking about a site, it takes time. If you know exactly what you want as a future land use, you can go rapidly to and finally address the points that you want to address. Field trial before implementation, it's necessary because you cannot reproduce in controlled condition the effect of the pest, the climate variability, and so on. You cannot manage. So field trial. Compare best conventional option versus selected phytomanagement. One, because if you are not successful, you have a backup to give to the stakeholder. Water supply is crucial. Create habitat, introduce, conserve biodiversity. It was addressed by Carlos. Account for the climate change, very important point. And you can manage that through agriculture practice, initial plant community, and so on. We have different tools for doing that. And take care, if you have slope, soil erosion, you can use terrace, which is very important. I would like just to dedicate today this communication to Petra Kidd. Jean-Paul Schwitzgebel, because he was one of our coordinator of the cost action, and he was really seeding and paving the way for many, many European projects. So it was important to cite this name. And like Carlos, I would like that the young people keep in mind all this work and continue and go forward. It's not finished, it's just the beginning.
Thanks a lot, Michel, for a fantastic presentation. One question, you have mentioned, well, we have discussed it a couple of times. Now the current scenario is phytomanagement under climate change. Do we need to do our experiments with irrigation with wastewater? I mean, instead of insisting of using water, shall we go ahead and do the experiments with wastewater? And which ones are the disadvantages of irrigation with wastewater from the point of view of plant growth?
Yeah, we will not use wastewater. We will use clean water, cleaned by constructed wetland. The purpose, the main idea, it is to, when you need water, and if you have groundwater, contaminated groundwater, or if you have some fresh contaminated fresh water but with contaminant, could be acid mean drainage or what you want. The purpose is to establish at the site also constructed wetland. You can clean the water and you can use this water for irrigation. That's the purpose. Most of the time, it's possible. I was working in Israel, I was working in Colombia, I was working in Ukraine. Yeah, just a minute. I would like also to give a support to people resistant at the moment in Belarus and Ukraine. I need to mention, I was there again in Ukraine and Poland at the beginning of this year. Yes, all these countries, we have constructed wetland at contaminated site, and then we were able to clean the water and reuse for irrigation, especially in Israel. Yeah, and about the plant community, yes, we have to adapt and to foresee what could be. So if poplar, people say poplar, they need water, but in fact they are also drought tolerant. It depends on the population. Willow, Salix caprea, is very resistant to the drought. Of course, Viminalis less. So we can design also the plant community according to what we want to do, according to the climate change. Yes, it's possible. Vetiver is very resistant. Nobody was thinking about growing vetiver in Angoulême, middle of the France. It's coming from Madagascar, but it's possible. Yes, now it's possible. And you can produce essential oil.
Do you have experience with creating habitats for higher animals? Is it possible under phytomanagement to look for habitat creation? Thinking,
yes.
Of course, not in mites and springtails. I'm talking about higher animals.
It happened in Samedar. We have wild boar, we have deer. It was necessary to put fences to avoid that the plants were destroyed by the wild animal, by the herbivory. Yes, it's possible. But we have to take care not only to, the herbivory of the foliage, but about soil ingestion. Because, when you have a rearing area, some of the animals, they are also injecting soil particles that are attached to the shoot, or sometimes they take a part of the vegetation, but with the root, because they not cut, but they take it like this, especially the cattle, the cow. So we have to take care about that. It is a soil ingestion. Because in the gut, you have acidification, and finally, you release especially the metals. So that's the main tricky point we have to target.
Thank you, Michel, for sharing your experience and good tips on fire management. So now we move to another working package, which is working on contaminated sites biodiversity. So it's a presentation that will take us to the Portuguese sites, presented by Helena Moreira. She's a researcher at the Portuguese Catholic University of Porto. He has a degree in biology and a PhD in biotechnology, and her research interests are mainly focused on the increasing plant resilience to abiotic stress and climate change through the development of an application of bioinoculants and working on remediation, phytomanagement of contaminated soils. After Elena, in the same group, we'll be talking Brais Hermosilla, who's working now in the the germplasm bank of the Olarizu Botanical Garden. He has a degree in environmental sciences and a master's in ecosystem restoration. So I'll present both of you, and you can start.
Thank you very much, Juan, and thank you very much to the other partners from the other universities. It was a pleasure to work with you all in these few years, and I'm very sad that this project has come to an end, really. I would like to go through to this kind of projects with you again, maybe one day. Maybe next year, I don't know, but I really enjoyed working with you. Thank you. And my team as well, of course, both Sophia's there would like to go through with this phytoremediation approaches in contaminated sites. And we would like to deep our knowledge about this in the future, in the next few years, future. So I'm going to talk a little bit about how can I, sorry, maybe I need some help here. I'm sorry. How can I, maybe,
You should see the screen.
oh, it's easier, of course. Okay. So I'm talking a little bit about the contaminated sites biodiversity. I'm going to make an overview about what we have done in in work package number 3, because we addressed the metal contaminated sites, and we addressed in the metal contaminated site the unique biodiversity that entails. And it's very important, this biodiversity, not only because it's intrinsic value, but we can also apply in different biotechnological solutions. So we have really a unique biodiversity. We have earthworms, we have a lot of plants, metallophytes, incredible plants. We have incredible microorganisms that we never look at them. We never know they exist, but they exist, and they are very important for soil functions. And we never address correctly, in my point of view, the biodiversity of soils. So we have really a unique biodiversity in these metal contaminated sites. And as strange as it may seem, we should preserve these metal contaminated sites because some of the biodiversity it comprises. No, I'm not good with this technology. Okay. So the WP3 was the identification and conservation of native biodiversity in contaminated sites for its potential exploitation in biotechnological applications. And we have 4 subtasks. The first one was the assessment of plant biodiversity. The second one was think about the conservation measures for plant biodiversity. The third one was the microbial strains that can have some biotechnological potential. And the fourth one was the assessment and the conservation of macroinvertebrate biodiversity. We have done this in 4 sites, one in Portugal, 2 in Spain, and 1 in France. In Spain it was Bandeira and Lanestosa. In Portugal was Borralha Mine, and in France was Saint-Amboulard. Starting by the assessment of plant biodiversity, I'm going to be brief on this because we had a lot of data. So we wanted to identify the plant species, mainly the metallophytic or endemic plants, identify their metal exclusion or accumulation strategies, then collect some data from the soil, and then evaluate the biomass, ecology, and possible uses of these plants that we identify in these sites. Starting by Bandeira Quarry, it's in the Serra de Meli de Careão. It's an active open cast quarry with ultramafic outcrops, rocks, ultramafic, so very rich in nickel, chromium, and cobalt, besides iron and magnesium. And here it was made a survey in 2 different sites. One in a forest area where they found some Quercus suber in the tree layer, some pinus, then the scrub layer with Erica scoparia, Ulex, Janista, and then some herbaceous layer, plants in herbaceous layer like Centaurea galesica, it's endemic to Galicia, Putentilla montana, Nocaia carolascens, and Lepidium netrophyllum. And the ones that, and in the quarry area, the vegetation was a little bit less abundant. It was scarce and sparse in the area. It was found the Silene uniflora, the Sagina merenoi, the Lepidium netrophyllum as well, and again the Nocaia carolascens. The 2 plant species that have conservation interest are the Nocaia carolascens, that is a zinc hyperaccumulator, and also in some cases of cadmium. And here we also have a capacity of accumulate cobalt in high concentrations. And then we have the Silene uniflora, subspecies uniflora, that inland only occurs in this kind of substrates. Regarding the Borralha mine in the north of Portugal, we have a former mine of tungsten, highly contaminated with copper, zinc, and lead. We made a survey in 6 different sites across the mine, mainly near the tailings. And this plant biodiversity was assessed over 1 year to cover the different seasons. And we found different trees, as you see. They are amazing. They are everywhere, despite the high concentrations of the metals that the soil has. So we have some Pinus spinaster, very ubiquitous species, Salix, very different types of Salix, Quercus, Betulus. We have several types of trees. Then we have some scrubs. Erica arborea can be used for phytostabilization, Agrostis capillaris that covers a lot the area. It's a metalloid excluder and is very good for phytostabilize the contaminants in the soil. We also have the Citizus, both Scoparius and Multifloros, that can be the Scoparius, both excluder or either excluder or accumulator, depending on the contaminants. We also have some cadmium hyperaccumulators, are very good for phytoextraction, such as Cerastium agglomeratum and Cardamina hirsutax. But they are quite ubiquitous. They don't need special measures to conserve because we have many plants in the area. So we identified 80 species and 49 had reported value for phytoremediation and can be used in the future approaches. Regarding Saint-Amboulard in France, it's a mining area contaminated with lead and zinc. They assessed the plant biodiversity in 4 different sites, and they identified more or less 27 plant species, and 7 species have a potential interest to conserve, namely Armeria muelleri, Festuca ovina, Uxinca alpina, Minuar taverna, and Agrostis capillaris as well. Regarding Lanistosa bress, we'll talk a little bit about this. in a few minutes. And then we have the subtask 3.2, which is the conservation measures for plant biodiversity. This, we are ending the project and we are still discussing what kind of measures we will do to conserve the plant biodiversity, namely in situ conservation measures, because ex situ conservation measures are being made by collecting the seeds and depositing the seeds in the germplasm biobank. That Bres will talk a little bit about this in a few minutes. Regarding the microbial strains with biotechnological potential, so we isolated bacterial strains from soil. We characterized it according to their metal tolerance and plant growth promotions. And the strains that we think they are very valuable and have to be conserved will be stored in the biobank. So what we have done, so we saw the most abundant plants or the endemic plants in the area and collected the rhizospheric soil, and then from that we isolated the bacteria. Then we assessed the plant growth promoting traits, namely the phosphorus solubilization, the ACC deaminase activity. It's a very important enzyme that reduces the stress in the plants. We saw if they produce siderophores, they are very, very important iron chelators. Then we assessed as well the production of a phytohormone that enables the plants to grow, and the production of ammonia. These traits are very important to promote the growth of the plants, especially in these deprived soils where we don't have so many nutrients or we have a high concentrations of metals and metalloids, and they are very important for nutrient acquisition. So regarding Bandeira, the isolation of this bacteria was made from Nocaia caroescens, this plant over here. We see the collection of the soil, and then we have there in that chart that we have 56 rhizobacterial strains isolated, and all of them produces these traits or show these traits, especially the production of indolacetic acid, the phytohormone. Regarding the borralha, we made the survey in the tailings from these plants that are shown here, and we collected the rhizospheric soil. We made a composite sample, and then we isolated 60 rhizobacterial strains, and then we had to select because there were too many. So the selection criteria that we followed was the growing, if they grow it up to 48 hours, because if they grow very slowly, when we deploy these bacteria in the soil, they would take a long time to thrive and survive. So for us, they would not be competent or competitive enough to deal with the other native bacteria. And the tolerance to metals, of course. And then from this, we restrained our selection to 37 strains. And we made the plant growth promoting traits. 100% of them produces the indolacetic acid. 54% were able to solubilize phosphorus, as you see in that picture, with a halo around the colony. And over 95% were able to produce siderophore and ammonium production. Regarding the bacteria from the other two sites, Santan-Boulard and Lanostosa, 52 rhizobacterial strains were isolated from Santan and 52 from Lanostosa. Several PGPB traits were made, and from those traits and the analysis, 6 were found that are very, very good in production, and they were trying to make consortia with them. So mix the bacteria, because sometimes when you use consortia of bacteria, we have a better effect on plant. Last but not least, the assessment and conservation of macroinvertebrate biodiversity. So we wanted to isolate native microinvertebrates, the ones that we found in those sites, namely the earthworms, slugs, and snails. They were then analyzed, the tissues were analyzed and processed and were stored in a biobank. So it were collected slugs, snails in several sites. In Borralha, we were not able to retrieve any animal, unfortunately. But the good news is that a new section in the Biscay Environmental Biospecimen Bank was created, was the mine microinvertebrates, where these animals were stored and were analyzed in several ways. Here are some pictures of the animals that were retrieved and their analysis, the process of the analysis. So in summary, we identified over 25 species, metallophyte plant species. Several were hyperaccumulators or metal excluders, being of particular interest for phytoremediation or better phytomanagement approaches. Species with an interest in conservation were identified, and their seeds were already preserved in the Olaris Luzern Plants Bank. Over 150 bacterial strains were identified, characterized. They were good, and from them were selected the best. I just want to say, sometimes the best in the lab are not the best in the field, but we have to start somewhere, and we have to select them somewhere. The most promising PGPB will be preserved or already preserved in ICAR and UCP facilities. Several earthworms, slugs, grasshoppers, and snails were also identified and preserved in the Biscay Bay Environmental Biospecimen Bank. This collection that we have is a repository for anyone that wants to establish a field and want to use these bacteria or these plants to install a phytomanagement approach in a contaminated area. Thank you very much for all the team members, not only from my team, especially from both Sophias again, but also for the other members, the PHY2SUDOE. I cannot rest, and I will say again, thank you very much. I learned a lot in these years, and I hope in the near future to cooperate with you again, or with anyone here in the room. Thank you very much.
Just a short comment for people who want to continue the work. It's not enough to store the seed, for example, for plants, because, of course, in the seed, due to the sexual reproduction, you have both the tolerant and the sensitive individuals. So it's very important to also conserve the plant population on site. When you remediate, keep at least a small area where you have discovered such interesting microbes, mesofauna, or plant species, because it is the only way to keep the population, the real adapted population. It's a very important point.
Yes.
Because if you restart from the seed, and if you especially restart on a clean substrate, then the sensitive will take over the adapted, over the tolerant individuals, and finally you will lose the adapted population. That's a very important point. So the repository for seed or for the animal, it's interesting, but it's not enough, okay?
We were discussing this yesterday, because how can we put some fences in the middle of the forest, maybe, or in the area, because we cannot do that. We cannot do. Instead, we have to be allowed to do that, to intervene in that sense. Otherwise, I'm not going to put some fences around the hyperaccumulator that is the only population that we have there. It's difficult. And putting fences, sometimes in my point of view, can attract some people that will destroy everything only for pleasure. So we have to keep them on site, but sometimes it's difficult. We have in our country some Drosophilon lusitanicum species, it's a carnivorous species, and they are not identified because I know people will go there and take them out. But one population, it was not Drosophilon because it's ours, it's another population of a carnivorous species, went out because of a fire. We don't have it anymore. So we have really to preserve on site, but it's very, very important to preserve in biobanks.
Thanks a lot. Do you have any favorite plant growth promoting trait? Because when you have 5 or 6 traits and 150 strains, the amount of work is overwhelming, you know. So do you have any favorite ones that you think they correlate better with plant growth? Because, you know, it's time consuming, you know what I'm talking about. I know that some people are in favor of deaminase activities, some other people prefer indole-acetic production, but do you have any favorite ones?
Well, I can talk about my experience. In the beginning of my work on this, in my PhD, a researcher told me that I was wasting my time. And I told them, no, why am I wasting my time doing the traits? Because I have to select, this correlates well. I know you're wasting completely your time, he told me. And now I'm not sure because I have done these traits under increasing concentrations because most of the articles make these traits without any metals, and we know that when the bacteria are with the stress of metals, sometimes the production is not the same, or they cease completely the production. And I made those tests, and it's like that. If I increase the metals, or I put the metal in the medium, in the growth medium, they don't produce the same amount. Most of them. Some increase, some decrease. And then I made an experiment in trying to relate what I have obtained in the lab with the results that I had with plants. What I found in one, not in one, more, was that the strain that produces the most was the best one in producing EAA. Was the lowest in producing EAA in the lab, was the best promoting the growth when I inoculated in the plant. So I could not relate anything between the traits in the lab and what I found in the plants. I want to know if they produce, but they produce much or they produce less. I have to select them, it's correct, but how can I select them? I have to start somewhere. Maybe that's the only way I know now, but I know I may not be selecting the best one. I think that one that the growth until the 48 hours, it's a very good one because it shows me which bacteria will thrive faster to compete with the other native, but the traits themselves are not a very good indicator, at least in my experience.
So we are still far away from having some rules to design a good consortium.
Yes, so in my point of view, yes. Yes.
Thanks, sir.
Yes, in relation to this, there are legal regulations that, for example, for commercializing a strain as growth promoter, they should have some traits. So finally, you have to demonstrate that
Yes,
not for our purposes that you can choose anything you have in your lab and you may have very good results with, as
No,
you
I
said.
think- yes, I think it's important to know if they produce or not. But if they produce a lot, oh, this is
Yeah.
the better one, sometimes it's not.
Yeah, yeah, yeah. Thank you.
Just a comment. Well, I believe that the best fence to preserve this special biodiversity, the best fence is the law, is the regulation. So we should try to combine the authorities to recognize that this special biodiversity is unique, could be very useful, not for us, maybe for the future. And if we protect these metalliferous or metallicolous environments, just not with fence, but just like a special biotope or this kind of approaches should be, maybe we can go further to protect them.
Yes.
As a matter of fact, there is a directive to protect metallicolous plants. Nobody can take it. So, but nobody paid attention to that, and they are maybe in very, I don't know, very abandoned places, as
Yes.
these mining places. So, and take the experience of other countries that they protect not only the biodiversity of these places, but also the industrial and other social benefits of this area. It's just
Yeah. Thank you very much.
So, good morning. I will introduce the work that we have been doing from Olarizu Botanical Garden regarding conservation of metallophyte species and creation of a germplasm bank in La Nestosa's mine. Or maybe not. Thank you. Okay, this is the index that I am going to follow. And first of all, I would like to introduce the mining area. It is located in the northwest part of Basque Country, near La Nestosa town. And in the aerial photo, you can see the zone that we have been working on. It is a mine that was abandoned in the 1970s. It was a lead, zinc, and cadmium mine. And it is formed, nowadays, it is formed by cliffs and mining pits and some dumping areas where in operation time they put all the debris that they were not taking. This has made that the metal-related habitats has had increased their extension in high amount. The objectives of our project are to study La Nestosa mine's flora, create a floristic catalog, and study their communities. We wanted also to recollect seeds from metallophyte and metalliculous species to create a germplasm collection. And also we wanted to suggest some in situ conservation measures to protect these species. Regarding the floristic catalog, we have identified all the plants living in La Nestosa mine, and we have identified up to 162 plant of vascular flora, where we can find 10 endemic species to this area and 10 species with phytoremediation potential. We had also analyzed vegetal communities. To do so, we have identified vegetation patches. We have sampled them, sampling up to 19 points. And we have created some abundancy dominancy tables that had helped us to frame these communities into phytosociological framing that helped us to identify up to 9 communities. Those are those communities, and here I would like to highlight the 2 communities related to metal habitats that are calcareous screes, that it's a community with a very scarce vegetation, with a lot of rocks in it, and with a really thin soil, and metalliculous grassland, that it's a community where grassland is more continuous and the soil is more deep. We have also mapped these communities, and I would like to highlight some of the species of interest that we found in the mine. We have been doing this work together with Ecofisco group from the University of Basque Country, and here I would like to highlight the behavior of some of them. For example, we had metalliculous excluders, we also had metalliculous accumulators, and our main species, Tlaspicyrulescens, or Nocaia cyrulescens, which is a metallophyte hyperaccumulator. With this knowledge, we wanted to recollect seeds to create a germplasm bank. To do so, we recollected up to 25 species around the mine. There are some photos of the recollection procedures, and these recollections were brought to our laboratory. Every recollection was clean, and we organized them. Here I would like to highlight that we tried to recollect at least 2,500 seeds per recollection per species. We have taken the opportunity to do some morphometric analysis of the seeds we have recollected, and here are some examples. After all these procedures, we wanted to conserve them in our germplasm bank. There you can see a photo of the bank, and the procedure we use to conserve the seeds is the dehydration and the freezing of these seeds. We put them in this type of test tubes, and only with void in it, and we can preserve them for long periods of time. At least we had some conservation suggestions for the species of interest. To do so, first of all, we have to identify limitations for vegetal development on the mine. One limitation would be slope stabilization. At some points, there are quite high slopes, and plants can have troubles in maintain their role in this soil. Also, the soil structure, as I said before, is at some points really low. And these first 2 limitations are particular to some points of the mine, but there is another limitation that acts in the total area of the mine, that is, it is the particular ecological features that the soil has. And I am referring to metal concentration. It sounds a bit strange, but this is the fact that makes these plants to live there, but it can also act as an impact, because at some point, even if it sounds pretty unlikely, it could be a mining reactivation, because the supply troubles that we are having nowadays, this mine could activate in the future. So we think that it's a really important fact that we could declare these areas as a flora reserve to protect these species. We also have another impact in the area, which is vegetal succession. These species are growing in grassland, so when shrubs come in the frame, this species got kicked out. So we would like to maintain these grasslands, and for the moment, traditional management it's doing so by grazing and by control the shrubs by fire. So after all this analysis, we have concluded that the Metalliculus habitats are well conserved in the Lanestosas mine. And as a result and conclusions, we have identified 162 species of vascular flora, 9 vegetal communities, and we have mapped them. This has given us an insight into their dynamics, and we have known better the species that live in Lanestosa. We have also collected seeds to create a germplasm bank of metallophyte and Metalliculus species, which opens the door to the use of these seeds in phytoremediation projects in the future. And as conclusion, after analyzing the communities and all the dynamics, we concluded that vegetation in Lanestosa is in favorable status of conservation. And I would like to thank Cofisco Group from the Basque Country University and all the people working on the project, and you for being here. Thank you so much.
Okay, thanks a lot. One thing I have not understood, why do we need to stop vegetal succession? I mean, why do we think that metallophytes in a grassland are better as compared to metallophyte shrubs? Is it important to stop plant succession and just to say, okay, we want to protect the grassland, we don't want to have a shrubland? Why?
For the moment, and taking into account the analysis that we have done, all the species with high potential of phytoremediation are in the grassland. So also we have to take into account that this mine has been, the activity on this mine has been stopped for 50 years now, and no shrubs had entered the main contaminated soils. So for the moment, naturally, no shrubs are entering this zone. I'm not saying that we will have to stop it, but yeah, for the moment, that is the status of the mine, and that is the knowledge that we know. Maybe in the future, some shrubs will enter in, and we will study them, and we will see that they have phytoremediation practical uses.
Okay, so we move now to the Basque sites, and they will be presented by Chema Becerril. He's the full professor of plant biology at the University of the Basque Country. He did his PhD in Massachusetts with the US Department of Agriculture in 1987. And he's currently leading the Ecofisco Research Group, which works on ecophysiology of stress and contamination in plants. Thank you, Chema.
Okay, good morning. Thanks for coming here. And for me, it's a very sad day and also a happy day. A happy day is because we can meet together after a while, but it's a sad day because we create a network we are working to create networks in the ecosystems that we create a network that it works really well. We enjoy a lot doing what we like with this research and trying to find solutions for this to remedy these soils. So we are going to present here the activities and results of the groups in the Basque Country. The groups, I have to thank the group of microbial ecology of Carlos and Lur, the group in the SEA led by Juan, the group in the university led by Manu Soto, and well, to all the people of my team. So in this project we have three main actions. One have been explained, the collaboration with the botanical garden in biodiversity, and the others is the long-term, or the former project is the long-term. Here I can see, and the other is we incorporate two new sites to be remediated. Yesterday, well, most of the work have been done because yesterday we visited some of these places. So you are going to recognize some of the places, and I am going to put some data of the things we saw just yesterday. Here the place, the Hundit place, Ariñet, we visit here. Well, this is as we found the place with pipes, a lot of residues, big ones, and construction, contaminated place, smelling bad, etc. So this place is in the belt, is where we just stayed yesterday. And here we select three places. Two degraded, but not with very high levels of pollution, and another contaminated, we'll see. This is the three places, what we call S5A, S5B, or S6. We yesterday visited and stay in this plot, in this emplacement, and we saw also this one in the site, but we didn't walk over there. So this is the places that we found. Is like we can see it here after a while when we implement some of the strategies of phyto management. And the things we made here is maintain the plantation, the analysis of pollutants. Another interesting thing we incorporate in the mainly by Thea and Naker is involve the people, the citizens, to work together to be part of the problem of the pollutants, to make a soil quantitative analysis of soil cars with a very simple parameters. The citizens could take part of the analysis and take part of the monitoring of these places. We also check plant biodiversity, and we are plant physiologists, so we used to check plant soil health, plant health and soil health also. Well, this is the part of the results of the citizen involved in the soil qualitative cards. The results are still wimpy in my point of view. We saw some increase in plant diversity and macrofauna in terms of macroinvertebrates over the years in this place, that it was really degraded, except in 2022. What is really very dry, you know, the heat wave and everything, it was really dry, and that brings lower values in all the physicochemical and also in the biodiversity of animals. Well, most of our focus we put here in this emplacement, the one we just visited yesterday. It was very contaminated, so we try to implement some phyto management strategies in the former project. So we check structural and functional biodiversity of microbial populations, plant biodiversity, plant performance. So I am going to show you some of the results. Well, because of the soil was so poor, after we take all the bigger residues, we have to put some amendments. The soil had no organic matter. So we have to put some organic matter in the soil. We also implement some biofertilization, but trying to put some mycorrhizal, commercial mycorrhizal, in this case, to the trees we plant. And we also assay crop diversity. So in the past, most of the strategies just go to plant only one species, but we want to check what happens when you put one herbaceous plant and one tree together, in co-cropping, what we call that. Well, so we have 6 treatment or intervention, or with alfalfa, with poplar, or the mixture of the tree and the herbaceous plant, or the inoculation, the combination with inoculation. Well, what we saw, the main contaminants in this place were TPH, PCBs, and PAH. And what we found in 1 year is, in general, only we found a reduction with the alfalfa plots, but not in the plots planted with the trees. As a matter of fact, we found also a rise of the contamination in this year. So, but after 5 years, all the plots, all the treatments reduce the pollutants, the organic pollutants. So it was degraded under the limits of regulatory limits. So only one plot is very close to the reference levels. We are talking about reference levels for other uses, which means the more restrictive use is for agriculture, because this is going to be a park, and well, with the levels even we have before, in some of them, they could be used. But in this case, we can say that the soil is clean. In this, I am not going to, we are going to, well, we perform some other analysis of microbial population, but Lur is going to talk about this thing with metabarcoding, just to see the structure, the structural biodiversity of microbial population in these plots, and check what happened in the other places of the consortium. And Lur is going to talk about that, so she will do good work. Well, when we check the plant biomass, of course, if you put alfalfa at the beginning, the biodiversity of this place decreases. And this, the plots with alfalfa have a very low biodiversity, and with the time, the native population is overcome over this culture and is colonizing these plots, so biodiversity increases with the years. As a matter of fact, now most of the plots are colonized by native grasses, and Planta olaceolata is the species more dominant in this place. And when we check the plant status at the beginning, when you put a co-culture of alfalfa and poplar, they compete. And as a matter of fact, we thought maybe it's not a very good idea, because our poplar were smaller in the plots with alfalfa. And, but during the years, the plot with alfalfa are the green ones. Now are the poplar with a higher height and trunk diameter. And also the photosynthetic area is one of the biggest one. And when we check, so now the biggest trees we saw yesterday are in the plots where alfalfa was first planted in co-culture. And when we check the photochemical efficiency, how the plants deal with light to do photosynthesis, well, it's quite similar. But if we see here the plants inducing photoprotective mechanisms, we see that the alfalfa and poplar plots, they have less photoprotective mechanisms. That means don't need to activate this protection. And the same, they have more chlorophyll and less antioxidant mechanisms. So that means that they are suffering less stress. We believe it's because the soil is so poor, and alfalfa produce biomass, fixed nitrogen, so the condition of nutrients in these plots are better than the other ones. But in any case, you should take in mind what Michelle said, that climatic conditions are really important. Watering the plants is really important until they are established. And this is very important. We cannot put the plants and leave it, because we are not going to be success with that approach. So from this emplacement, we can say that we came from a brownfield and now it's becoming a greenfield, free of pollutants. We partially recover soil health, increasing microbial properties of the soil, native plant biodiversity, and now we have a permanent healthy trees over there. And one interesting thing in the way is that the eco-culture between one leguminose, fixing nitrogen, and poplar could be a good strategy in the long term. Maybe not in the short term, but in the long term, yeah. Well, the other new sites is, one is in Zumabacocha. We yesterday was walking down this road, or let's say road or way, and the other is in Guernica. Guernica is near the coast in the Basque Country. Both are peri-urban sites with mixed pollution, and we could do these approaches because they have low-medium contamination, mainly by organics. So with the phyto management is going to work much better. So both are landfill. This is for dumping site for construction and demolition and pesticide residues. The other is for sewage sludge and pesticides. In the one we visited yesterday, we found that the concentration of contaminants, mainly TPH, PCBs, and PEH, and pesticides, were really heterogeneous. The heterogeneous in the place they are, heterogeneous in the concentration they have. So we thought we cannot make treatments. We should look for another approaches. So the first thing was just take out all these big residues, just do soil movements just to make the plantation, and put some plants, in this case trees or herbaceous plants. So, and the approach here for to looking for a solution is something that you heard just yesterday, today also, is why don't use a plot is a ecological niche. Why we are not going to use one vegetation, one special vegetation for this place? So in this case, is meeting ecological restoration with phytomanagement. So in this case, the strategy was to choose what is the best plant for this plot. Because of the edapoclimatic conditions, because of the future use of the place, in this case is going to be a park, so we have to imagine here a forest of oaks, here a forest of fast-growing trees, here's a prairie, etc. So, and this is the treatment, let's say that way, that we use. Is we try to establish a holm oak forest. So yesterday we saw small trees, but we can imagine that maybe in 10 years. And the other is a meadow, gold oak forest, willows and poplars, and scrub. So using scrub and bushes from the Mediterranean area. So we analyze the soil, we make the soil quantitative analysis with soil cards, the citizen science involving citizens to do that, and the vegetation, the biometric or physiological parameters. So this is at the beginning when we put the plants with the different strategies we implement. This is the concentration of each plot with each contaminant. This we have pesticide and PEH, this TPH, etc., and different concentrations. So this is how it appeared. Well, 6 months later or something like that. This one was in autumn, this one is late spring, something like that. And at this point, with this not many, it didn't pass too much time, but we were able to reduce the contaminant in most of the plots, except these two ones that are really close to the reference levels, but it's okay. We check, this is the soil qualitative analysis of soil cars, and we say that the seasonality have one importance, so spring seems to be the best seasons just to increase soil physicochemical properties of soil and also the biodiversity of macroinvertebrates. And if we check what happened with the soils, meadow seems to be the treatment to increase much better the biodiversity of animals, but the worst results was obtained with the Mediterranean shrubs, bushes we put there. Checking the vegetation, well, we follow the height. This is the first step, just to characterize the vegetation. Fast-growing trees have better grow in terms of height and also in terms of photosynthetic area. As a matter of fact, it's something curious because the number of leaves is very different between all different species we planted there. But when we check, we found a nice correlation between the photosynthetic area and the height. So we can measure the height at these first stages and calculate more or less what is the whole photosynthetic area of the plants. So when we check the photoprotection mechanism to see if the plants are under stress, in general the photochemical efficiency is okay. That means that they are performing very nice photosynthesis, but this is because they have very good photoprotection mechanism and also the level of antioxidant are really good. As a matter of fact, there is not too many difference between the very well-adapted plants to dry, like quercus or something like that, and the fast-growing trees. So they cope with protecting their physiologies. So the works done in Guernica is very similar, is a peri-urban with mixed contamination. The thing here is that is a sludge landfill, a landfill for sludge and some pesticide. We characterize the place in several points, and we choose the most contaminated place just to make a pilot assay of phytomanagement. Well, the objective is to reduce the level of, in this case, organic contaminants and select the best biological treatment, let's say that way, and reduce soil ecotoxicity. So we choose the worst scenario, and in this case we are going to implement compare three kinds of biotechnologies. In this case is phytoremediation, bioremediation, and vermiremediation using earthworms. This is the experimental design that we make in this plot. Using, in this case, we put a Medicago sativa, a bacterial consortium that it resolves really good degrading organic contaminants, and Eisenia fetida, and the combination of all of them. First, we put the plants in spring, and then in the next autumn, we put the worms or the inoculum with bacteria. And this is what happened. In 1 year, this is the first year, and this is after the treatment, 1 year later. In all the plots, the levels of the contaminants was reduced, but the best treatment, the combination of the three technologies, bioremediation, phytoremediation, and bioremediation, it was the best treatment. In some plots, the level of dieldrin decreased under the regulatory limit, but we have several problems to reduce the level of cadmium and benzopyrene. We did that. We check the toxicity of the soil, and this soil was really toxic for worms in different parameters. I am not going to explain each one, but the best treatment, the best increase was when we use all the three technologies, biotechnologies together. The same with plants. Sensitive, we use generally cucumber, is Cucumis sativus, because it's a very sensitive species. So even the more sensitive species increase better when we put the three treatments. But we don't found any response when we check microbial properties. In this case, it's functional biodiversity of microbes. As a well, we explained that because we check the native population of these places. So they are well adapted, so they don't suffer a lot with the changes we made with the phytotechnologies or biotechnologies. Well, because the three technologies together work really well, we expand this from this pilot experiment to other areas less contaminated than this one. Well, and here it takes a long time to do that, but native vegetation overcome over our culture. So we put one plant, but native vegetation, and it's because it's a very flooding place. So the native vegetation there and some, in this case, some trees grow really well, in this case, Salix atrocinerea, as this plot. You see this big circle means the biomass, the amount of biomass. And we treat all the points except this one. This one goes our control and have very small biomass. So it is a very curious thing, have very small biomass, but a lot of biodiversity. They grow, plenty of species grow there. But in the other ones, they are dominated by one species mainly, in this case, by Salix. And as a matter of fact, it was the best phytoextraction rate was found with these trees. So sometimes we should observe nature and see what is the best approach. In this case, if we could recommend Salix atrocinerea because it colonized the place really well and have a lot of big biomass and reduce the levels of metals in this place. This is in red is contaminants overpassing the reference levels. In 2018, we made the treatment, and in 2021, all in green is that the levels of the contaminants were reduced, and 1 year later, only in some plots remain some of the contaminants. In this case, benzopyrene, and cadmium is the main contaminant here, but we were able to eliminate all the eldrin, 42% of, in general, 42% of benzopyrene and only 20% of metals. And well, this is a combination, this is a redundance analysis, a B-plot of all parameters. And you see that the phytoextraction goes with the plant biomass and microbial biomass. They are going together, so they are really very good related. And soil toxicity is for the point we didn't treat, is what is nice at this point, because that means that our strategy works in some way. And I would like to finish, just thank you all the people here and all the people who made together our network, and especially to the people to the trinity of this project, what is Petra Kidd, Carlos Garbizu, and Michel Mensch. And well, I hope that in the future could we collaborate, as Elena said, because it's difficult to create an ecological network, but it's difficult also to create a network to work together in this field that I believe has a lot of future. Thank you.
Only one question for Becerril, for Professor Becerril. When you determine that some of the plants are stressed according to the biometric parameters and the biomarkers, do you also observe a higher incidence of plant diseases and pests But have you ever been forced to apply pesticides or not?
No, I don't think, no, because the plants that are activating this photoprotective mechanism and produce more antioxidants, they draw part of the energy to do that. They can survive, but they don't grow so well. So as a matter of fact, it's very good. The correlation between that the biometric parameters, they are healthy in some way. They have chlorophyll and don't have pests, but they grow less.
Okay, so finally, I will present a little bit from the perspective of local administration why these fire management opportunities are so interesting to deal with public soils. Well, you know, I'm Juan Vilela, I'm a forest engineer and a landscape architect, and I work for the Center for Environmental Studies of Vitoria-Gasteiz. We are a little bit late in the program, so I will try to be short, and I propose to move forward 30 minutes, so we have time for the coffee and to rest a bit. Thank you for your patience this morning, because it's an intense section, so mine is going to be lighter. I'm not a scientist, I'm more like a civil worker, so it's going to be more light, I hope. It has, okay. So, just a context where we are in the north of Spain. As many other Mediterranean cities, the city of Vitoria grew a lot in the industrialization times, very similar to Milan, as we saw yesterday. But even though the city of Vitoria is very connected to nature and is very compact, we see the mountain range in the bottom, the agricultural lands and the urban frame, and that's more or less 1/3 of the surface of municipality dedicated to its use. But as we see today, you know, the green city was not always like that. In the 90s, in the periphery of the city, we had a lot of environmental problems, flooding, polluted soils, illegal activities, as the case of Milan yesterday. And in that time, more or less, was created the Center for Environmental Studies to try to deal with these issues. They come with a sustainability name. In those days, it was a new thing. Maybe the most iconic image is the green belt. You know, this system of parks that surrounds the city, and they reclaim the biodiversity and the potential for conservation of those direct lands in the past. But now we also talk about the yellow belt, surrounding the green one, which would be the protection of the agricultural lands. We pay attention to the soils and to the functions of food, you know, in the global change epoch that we live. So from the origins of the idea of the Greenbelt as a multifunctional landscape, the focus was on biodiversity conservation, environmental awareness, and public use and recreation. But in the year 2012, when the Green City Award was given to the city, we came with the idea of coming from the Greenbelt to the green infrastructure system, to understand it as a network, as an ecological network. So we came with this plan to bring nature inside of the city, into the city. And as you see in the picture on the right, there was a series of connections and corridors to try to bring, as in the picture shows, finding these ways for nature to come in. This is a scheme of how to intervene in the different sections of the city, from the medieval town with micro landscapes to the new neighborhoods with patches to the green belt. And the green infrastructure system, the strategy was accompanied with a series of projects, more than 100 projects of any size. Today we just give some examples of the area in the Jundiz Park with the PHY2SUDOE project that Chema explained really well, and the Lasarte pits in the bottom. So starting from Jundiz, which we visited yesterday, it is located in the east of the city.
the idea was to weave the territory that was broken. But in the upper picture, you see also that we are working with contaminated soils. This is the maps of the polluted soils. I won't get into detail here because we just saw it. Just mention that we've been doing this phase by phase, thanks to the help also of the Basque government, financial aid given because we were fighting the climate change. So we accompanied all these phases with the calculus of how much carbon per year we can sequester based on the treatments we do on the soils and the plants we plant. More or less the place was like that, just a derelict land with landfills, and now it looks more like this. Some pictures just to show the evolution of the landscape. We explained that yesterday, that we try to reuse any material that we have, avoiding taking out the soil to another place, the effort on increasing the organic matter, and the steps that also Chema mentioned to come from the previous state to the final state of the PHY2SUDOE treatments. Also, the phase 3 included these areas where we have the experimental plots. So it's a restoration, but it's an experimental site. We need to monitor it, and we also use it as an educational tool. Every year we have 2 or 3 visits of students or people like you that come to see it, and I think it's a nice visit to do. So I'll just bring here some pictures of the previous state and the current state, just to see how it changed in time. Well, mentioning that we are now hiring or contracting phase 5, which will work on the south of the area. And moving to Lasarte pits, this is looking more to future steps or to the future. The Larva Gorri project is projected in the south of the city in an area that really would close the greenbelt. We have an idea, concept idea of what we want here. We have the problems of flooding and the soil pollution, much higher than in Hundit, so it's a more complicated site. And also, it is a privately owned place, so we have to deal with that. And we are looking at different perspectives to work with that. And that's why yesterday we brought so many examples of collaboration of public and private businesses to try to deal with a problem that is for everyone, for every citizen. Just to mention that since we are not now working on the earthworks or implementing the project, we are doing a lot of investigation to have the best data we can to make the best choices in terms of later designs. One of those is the investigation of the hydrology and the geological model, because we have 2 layers of subterranean waters, one that runs faster in the permeabious upper level, and then one runs slower. And we also found that we have an influence of the landfill of the city, which is in red in the right picture. So the good news is that we started doing things in collaboration with URA, which is the water department of the Basque government, in one of the gravel pits that was not so polluted. Here we only had 2 points of pollution, so this was one of the pits that didn't get so many residues deposited. And these works are on their way this year. So they just provided us with this picture, so you can see this is going to be a pond for flooding prevention. We're taking the clean water to the river, not to the water sewage system that was before. And an interesting thing is that first, they let us, or they let them reutilize a lot of material inside of the site for construction purposes. Basically, they could deal with the contamination inside, taking out some hazardous materials. The rest of the soils were done. So I think we're moving forward in the idea that we want is to work on in situ. And they took also into account to preserve all the patches of vegetation that are there, trying to, even it's a hard work with machinery, they respected the natural vegetation, because we know this place will be a high biodiversity spot in the future, And in terms of landscapes, it helps a lot to preserve the existing vegetation. So I'll finish with that. And thank you for your attention and patience. And I may take one question, and I think we can come back later at 12 o'clock. Do you agree with that? So we have 30 minutes to rest.
And what do you think about the proposal by some people of incorporating all these urban green belts into the carbon farming market hype or whatever? Some people are proposing also to incorporate these urban infrastructures into the, the carbon farming hype. What do you think about that?
I think we should take all the benefits of, using the plants. I think the plants are the tool number one to fight climate change. I'm saying plants in general, not only forested areas, that the ones we see here, but also the agricultural crops. Actually, I didn't mention it, but in Jundiz, we invited some farmers to harvest and to use crops as a way of to manage public land. So it's a win-win situation, in our opinion. I think maybe Manuel can say something about that, because we have the idea of working in that strategy, right? You want to mention something?
When it comes to carbon,
Thank you. So for those who don't know me, I'm Imanol. I work together with Juan in the Center for Environmental Studies. And when it comes to carbon, at the moment, our attention is more on fertile soils. We looked a lot on the forest. We have also some measures for the green areas of the city. But we know that the biggest potential is on fertile land. We see those as sponges that have been kind of replenished from, not replenished, emptied from carbon in the last decades. And we are also waiting for this new law on soil health that is coming, to see whether that is going to push a little bit the management that we give to those soils, and see how much we can store on those soils, right? One of the motivations that we have to push this strategy is also this mission that Vitoria-Gasteiz as a city has been selected by the European Commission to be one of the 100 case studies, or guinea pigs, maybe we could use, on accelerating to the carbon neutrality, instead of by 2050 achieving this carbon neutrality by 2030. So carbon storage is an important aspect that we need to work, because we are asked to reduce emissions by 100%, but then they allow us 20% of that to be stored in carbon sinks. So quantifying all these carbon sinks is a line of work that we are doing at the moment, and we see the biggest potential on fertile soils, because the forests that we have in the municipality are not managed as the forests in nearby provinces. So we understand they are storing kind of a constant amount of carbon, and they reached a little bit the top of what they can absorb. The green areas, a little bit the same. We are also quantifying that, but then the biggest increase we see on soils. So that's a little bit the line of work that we are pushing now.
Okay, thank you. So let's see here at 12 o'clock. Okay. Coffee time. second section of the talk. Now we have a section for another European projects that are dealing with the same trouble in different perspectives. So we will start with Rocío Barros. She is a biologist that did her PhD in the University of Zaragoza. And now she is the leader of the Environmental Sustainability and Toxicology Group Research at the University of Burgos and the coordinator of the Greener Project. So, Rocío.
Yeah. Okay. Now reduce the time to 7 minutes, so I will try to be fast. So, Juan?
1 minute.
Ah, okay. So, well, just before the start, I would like to thank Juan for the invitation, and also I'm very happy to be here, also to see and finally know some people that we were exchanging emails, and we know in some online meetings, but well, as Cain or Juan, that they are sharing with me this part of the session today, so I'm really happy to be here. So, what I'm going to present is the one European project, is the Greener project that was founded in 2019. So we are almost in the end, so I'm going to give you a very brief introduction of the project and very brief introduction of the main results. Well, it's a collaborative project funded with 20 partners, 4 of them from China, so that was a very big challenge in the project to deal with the international collaboration, not within Europe, I mean, you know, within Asia, and also because of the partners didn't have, I mean, the partners from China didn't have any funds, so that was a very big problem in the project. So, well, this project, I think we don't have to stop in this part. We have funded this project because we know that the contamination is increasing, so we wanted to look for new bioremediation technologies, focusing mainly in the integration of different bioremediation technologies, like trying to find the different efforts of the different remediation technologies in order to accelerate the remediation time and improve the efficiency. So, well, regarding the main objectives, first of all, we were working in the selection of the different polluted sites around Europe and China. We have been focused in developing different individual bioremediation technologies and then focusing on the integration of these remediation technologies, always taking into account the scaling up of these technologies. So, and finally, by the end of the project, the idea is to demonstrate that these technologies are able to go into the field. Well, this is the work package structure, so it is not necessary to stop there. So, well, we have been focusing in different remediation technologies for water and for soil. So, in the case of water, we have been working in phytoremediation, and the integration of the phytoremediation with the bioelectrochemical systems. Then different bioelectrochemical systems, microbial fuel cells, microbial electrolysis cells, in order to eliminate or degrade different types of contaminants as antibiotics and pesticides. So mainly they were focused in metals, acidides, antibiotics, hydrocarbons, and pesticides. Then for the soil, we have been working in how to improve the bioaugmentation, I mean the biopiles, the bioaugmentation and the biostimulation, and also how to integrate this with the phytoremediation, that is also something that you have been explaining today, and how to do this improved ecopile. And also, finally, if possible, to integrate this with the bioelectrochemical systems. The project was the aim of to scaling up all of these technologies, always taking into account the legal and safety aspect, ecotoxicology evaluation, and also the sustainability aspect. So we are now ending the project by the end of August, so it's the 4 years of Greener. So as a summary, we have been working with 13 remediation sites, 12 in Europe and 1 in China. We have been developed 13 remediation technologies and 8 hybrid systems including multiple technologies that have been successfully developed at laboratory scale. One thing that I would like to remark is that also we have been working in a 5-step decision tool diagram for scaling up of the technologies, because sometimes when we are working in the lab, we are not taking into account how to go into the field. That I really like the PHY2SUDOE because you were really working in situ, showing how these technologies can be really implemented. So, well, we have been selecting different KPIs for each technology in order to really know why or how a technology is working, and also, if this technology can be scaling up, taking into account the operational parameters, the sustainability aspect, techno-economics. So, well, that is something that that I think it's quite interesting, and we are working now in how to publish this methodology that has been developed with the company Tau, that is a environmental company in Europe. Well, this is more or less the results, the technologies, as we said, that we follow this scheme, laboratory scale, pilot scale, and then we go to the field. So that was the technologies for water. And just to show you one of the technologies that you have a poster outside, that my colleague Akif Hassan can explain you in detail. That is how in the University of Burgos now we are integrating these constructed wetlands together with the electrochemical systems for metal removal. So I'm going to the soil part. So we follow exactly the same structure, lab scale, pilot scale, and field scale. And just to let you know, in the case of the bioaugmentation and biostimulation, we have been working with different technologies like vermicompost that you already mentioned today, biochar, different surfactants, biosurfactants, but also we have been working in development of carriers based in colloid biology. So how this new methodology or new technology can improve this relation of the bioaugmentation part. So I think Carlos mentioned this morning that it's really important to understand which is the microbiology of the soil. So for the soil, we have been following this methodology. So we have been analyzing the microbial community of the soils. Then we have been doing the metagenomics, metatranscriptomics, metaproteomics data. And then this information can support us in the development of these smart carriers or development of synthetic bacterial community. So, well, this is just an example of the phytoremediation together with bioaugmentation and biostimulation that has been developed in Carlow in Ireland. So here it was really nice because they started at the beginning of the project with this with 7 ecopiles. So these ecopiles is just like a biopile of soil in which they have inoculated some microbial community, and then they put the plants, and what they have been done is to analyze what is happening inside these ecopiles during 3 years. So this information is being used to develop a version 2 of these ecopiles to improve the technology in terms of efficiency and time. In the case of bioaugmentation and biostimulation, we are working with the construction company Acciona, and well, these pictures are for this Monday. So we have just started to demonstration of the technologies this Monday, and as I said, well, we have been tested previously in the lab, and now we are excited to see how is the results when we are going to the field. We tested at 1 ton, and it was good, but now let's see what is happening in a big. I'm late, so very fast. If you want to follow us, these are the social media, and just I would like to introduce Biosismo is the new project that we have started last September. It's the sister project of SymBioRem that is going to present later by Juan, and we are continue in some of the research that we started in Greener, but I think that something that is very interesting is that this project also follow what Carlos was saying this morning, because the objective of the project is to develop biosystems between the microbial community and the different bioremediation technologies in order to have like microbial assisted phytoremediation. And just to end, the different EU projects that we are working in that have been funded in the similar calls. We are organizing a workshop on the 28th of June in Switzerland. That is the day before the BioRemit will be start. And well, you can see that we are 7 projects, and the idea is also to have we will have first the final conference of Greener, and then we will have this workshop in which we'll have also a roundtable in order to set up a network for the future. And yeah, that's it. 2 minutes later. Yeah, if you have any question. No?
If I understand well, in your eco pile, you are planting also.
Yes.
But did you inoculate also with, endophyte or rhizospheric bacteria?
Well, it was not, I think there were not exactly PGPRs or PGPBs. I mean, it was, they have insulated from the soil the microbial community, they enrich it with the hydrocarbons, so they select the consortia, so they do a bioaugmentation. Also using different bacteria from previous projects, so they have a kind of consortia. But it is not, I mean, they have not tested it has any effect on the plant growth. It was just like, to see the interaction of for the degradation of hydrocarbons, because it is not metal, it's hydrocarbon removal.
About the flue cell.
Yeah.
Did you see a decrease of the availability of all the organics, or maybe sometime you can increase the bioavailability of some organics?
I get your...
I mean, using this technology of the cells, chemical
Yeah.
cells,
Okay.
when you put a substrate, a real contaminated substrate, one of the potential effect can be to separate the organic matter and to open the microporosity. And maybe one side effect can be that you, the aging is counterbalanced, but the reaction, and finally the contaminant, the organic contaminant became much more available than before.
Yeah.
So do you observe that, or?
Well, what we observe with the when we include the in the case of in the eco pies, what we included was a kind of passive beds, bioelectrochemical system with it was a graphite road. What we observe is that we are not using this integration because it's not working, okay, first of all. But what we observe, now it's true that we are studying what happened, but we observe is that there is like a 20 centimeters of diameter around the graphite rod in which we cannot find the plants. So, there is, like, as you said, probably there is a kind of, electroactive chain, and then it is, it is not a plant growth. So probably, yes, it's sure it is, something has happened, but it's true that we don't know exactly what. Yeah. And in the case of soils, it is true that the bioelectrochemical system has been working very well in water, but for soils, it has been, they are not going to the field because it is not, it's still ongoing, and it is supposed to many projects, to many problems. Yeah, the scaling up and testing the technology of bioelectrochemical systems in soil. Yeah.
Thank you, Rocío. Now we will hear about the Poseidon project explained by Caen Quejigal. He got his master's degree in analytical chemistry in the University of the Basque Country, and he joined the team of Tecnalia in the year 2000. And he's been working several years in projects related to soil, sediment, and groundwater remediation. So he has a lot of experience, more than 20 years in European projects, and has made several publications. So, Caen, thank you.
Okay, good morning. Thank you very much, Juan. Thank you very much for the invitation for presenting Positron in this event. To the PHY2SUDOE project, and particularly to SEA, which is the link between the both projects. So it's nice to be here today. Once again, really short slot, so I will go for key messages and some ideas, and later we can discuss in the event or in any other moment if you have any interest or whatever. So I will go very quickly through the project. Okay, so the main goal, the main idea of Positron project is to deploy a process of pre-commercial procurement in order to promote new developments related to remediation of cell contamination, mainly brownfields. And the idea, the key point here is to try to concentrate, to aggregate same or quite similar interests from different public bodies with, let's say, similar brownfields or something like that in order to push together for a new solution, giving a response for many different places all over Europe, hopefully internationally, of course. So with that idea, the project has a main group of different buyers group on two different levels, two front runners, which is the Port Authority of Trieste, and the other one is the Bilbao City Council. We have a representative from Bilbao City Council here, Jorge. And the second level of three observers with less involvement, let's say, in terms of mainly funding of the project and the activity, including CEA, SPACUE in Belgium, well, Wallonia, to be more precise, and Biotejo in Portugal. Additionally, we are other partners. Tecnalia, for example, is supporting the technical process and so on of the process of the different solutions and so on, and expertise in that procurement processes and legal administrative requirements and so on. But it is more or less the idea. So the project has two main interesting points in terms of innovation. Let's say one is the technology, of course. Another one is the process itself. I wouldn't say that PCP is a new process, of course, because it's really implemented in some particular countries and some particular sectors, but maybe not in our common field of study, as far as I feel it. So for me, from my own experience, was very interesting to face research projects in a different way. I mean, our common practice is to go for a topic in Horizon 2020, Horizon Europe, Life, Interact, whatever, fighting for the proposal, wait for resolution, happily you are funded, and then I wouldn't say you relax, but let's go for the project for the next 3 or 4 years. This is not the scheme. This is the difference. You will be competing all along the whole process of the project. So for you to understand, we have 3 different phases in the project. The first phase, where we receive, I think, 13 different proposals for solutions for the challenge I will present later. 8 of them were funded for a first phase in order to define a robust solution. Then 4 were funded for the lab pilot and lab scale demonstration and so on. And finally, only 2 are currently working in the field sites in Bilbao and in Trieste. So it was really competing process, really interesting. So first key message. I know maybe you are not the best audience for this idea, but if you know a public body who is a site owner with a similar problem, a quite similar problem, please feel free to present the project in order to enlarge our group of buyers in the context, not in the main project now, but in the near future, well, out of the scope of Positron, we will have a next stage for a continuing this kind of idea. So please disseminate as far as possible for you in order to register in our website for sharing this kind of problems and find a solution jointly, in a jointly way. So the challenge that we formulated at the beginning of the project. Well, the idea is to seek for a soil remediation solution, considering life cycle approach, cost effectiveness, of course, prefer as in situ solution, or potentially on site at the beginning, capable of decontaminating at the same time organic and inorganic pollutants in a context of anthropogenic materials. And, well, more or less, they are brownfields, as I mentioned, including mainly TPHs and PHs, and also heavy metals, mainly arsenic and lead. Also, additional heavy metals has included in the processes and the research, but this was more or less the key challenge at the beginning. So here we prepared a conceptual model at the very beginning of the project in order to understand, of course, with a particular hydrological condition, because all of them are close to, let's say, estuarine or marine environments with a certain condition of hydrological environment. So, to be honest, at the very beginning of the process, Tecnalia as a research center, we had to decide if go for to be either on supporting the bias group from a technical point of view or competing in the process. So we thought, let's go for the easy one. Yeah, joking, of course. My bosses decided that position. But anyway, it's very challenging. I mean, the approach is really challenging, but was the idea of the project from the very beginning. So we are, as I mentioned, at the third stage of the process, which means that the contractors are operating in real condition. We have sites in Bilbao, in Zorrozaurre, in the north part of the island of Zorrozaurre, and also in an area of the Port Authority of Trieste, testing the two final solutions at the same time in two different locations. As you can see, we have plots of, let's say, more or less 500 square meters, more or less 3 meters deep, but more or less the structure and the idea and the approach. So here we have a very brief summary of the two solutions competing at the final stage. I know that it's the most interesting for you to know about these technologies, but both of them are in the process of knowledge protection. So I can share only just a brief idea of an overview of the solution that they have been testing. They are testing now, and also you have in the website short videos of both technologies where you can get some additional information, but not too much. But to have an idea, the first one is soil omic technology that, well, the main innovation is related to the using of new developments concerning metagenomics approach. To be honest, when I first read this solution, well, I know most of you are biologists and a chemist, sorry for that. So when I started reading this approach, for me it was something like science fiction or something like that, because they use some kind of accelerated characterization of genetic material in the autochthonous microbiota of every site, and in that way try to push and to stimulate in a better way, in a more efficient way, the activity, but the bioactivity of the site. But I cannot give you much more details. So this is more or less the first idea, the main innovation. And also the second one was, here more or less the innovation relies mainly on the combination of many different currently available technologies. But as you can see, the challenge is really complex, so the solution must deal with very different technologies, different capabilities in order to respond to the different challenges of the formulation that I have just presented. So they work mainly with an electric fields in order to mobilize some of the pollutants and other components of the soil, but combined at the same time with chemical treatment and also biological activity. well studied and previously defined in the lab and the prototype that they have been carrying out in the stage 2. So I cannot tell you much more about both technologies. This one has finalized the field testing, so we're really excited waiting for the results in order to understand if the final analysis and so on are promising in terms of technical fulfillment of the requirements, in terms of economy, cost, in terms of sustainability, and so on. And also the second one, the previous one, is up to finalize these days, so we will have final results hopefully in May, where we'll be evaluating, assessing the final results and having a more clear idea of the capabilities of these two solutions. And hopefully we will have a final conference in September in Bilbao, where I would like to say that we will have more details, more results, and certain, I don't know how to explain, a more clear idea of the potentiality of these solutions in the market tomorrow or in a couple of months or in a couple of years. So more or less the approach of the project. Thank you very much. Do you have some question?
Muchísimas gracias. Maybe it's a conceptual comments. And the point is, what is controversial, it is the soil decontamination. When you have a future land use, for example, you want to establish a new building area or any industrial plant or what you want, you will have a capping with concrete and only green corridor around. You don't care to decontaminate the soil. And even more, if you have aging and that the PAH and PCB are well polymerized, why you want to decontaminate? Because you don't have exposure pathway. So you put a lot of money, and finally, it's better to do nothing at such place, for example. So, do you consider the bioavailable fraction? Do you consider the exposure pathway? Do you consider the future land use? All these things, stop here because it's a large debate.
Yeah.
But we can discuss a lot about really soil decontamination, and if it is necessary, my opinion is we need to think more what we want to do, for which zone, which reactive, what are the exposure pathway, and not only invest a lot for decontaminating something that if there is no exposure in the scenario of the future land use.
Completely agree, absolutely. The point that we formulate the challenge with the BIOS group, thinking about the future of that site and in terms of what they will need. Of course, they need advice. Then in terms of technical, I understand your point and I share it to a certain point. But I mean, it was not our aim to be contaminated by itself, of course. The point is that in the areas we're operating now, in the near future, there will be parks, there will be residential areas. So we are trying to develop solutions in order to answer that requirements in the future. Of course, at the very end, you will need a case-by-case study and what you need to deploy and what will be your target in the different case studies or wherever. But our intention, our aim is to have the technological ability to be versatile in somehow in order to respond the different challenges that every case study, every location, every brownfield, every future park or wherever will need. But I know that we are trying to to deal with a very large different case study. I mean, it is problematic, and I share your point. Yeah, definitely.
This is not for you, it's for Michelle. You are very, very, very welcome. Bienvenue. Have a discussion about that with our authorities. It would be very interesting and very constructing, I think.
I mean, if I solve the question, in fact, it is education of stakeholders, and different case tools, because there is no general rule. We need to be flexible and to adapt to the different situation. That's the way. And okay to discuss, no problem.
Unfortunately, nowadays in the Basque Country, we are linked to a very strict and very far from being flexible authorities. So we are ruled by numbers. There is no case by case. Sometimes in investigation sites, for example, we see things when every time I come here, for example, I wonder, and talking with Juan, I tell him, when will the authorities let us, the people who live in the real world, do that kind of things? And I guess that it's going to take a long time to arrive to that, if we really arrive to that one day. So, well, I appreciate very, very much your opinion. I agree, but that's our situation here, at least, at last.
Okay, so to close this section, we will hear about the Symbio-REM project. We invited José Luis Vilas. He's an associate professor at the Physical Chemistry Department of the University of the Basque Country, and he's also the head of the Macromolecular Chemistry Group. His current research is on basically on polymeric materials, and he holds more than 100 publications and 3 patents. Thank you, José Luis.
Perfect. Good morning, everybody. Egunon eta eskerrik asko Juan ekitaldi hontan parte hartzeko gomitatzeagatik, placer bat dela beti badakizu, ezta? Zuen artean egotea, batez ere kimikalaria izanez. Zio zera raro izango da hemen. And thank you very much for the opportunity to present the Symbio-REM project. As Juan have told, I'm José Luis Vilas. I come from the Macromolecular Chemistry Group at the Physical Chemistry Department of the University of Basque Country. And we are a group devoted to polymeric materials, to plastics. So it's quite strange to be here or to be in this kind of project. Well, we have a special, I don't know if it's too special, research line where we use plastics to try to remove pollutants in soils and in water. And for this reason, we are part of this interesting project, Symbio-REM. Symbio-REM is the acronym of Symbiotic Circular Bioremediation Systems and Biotechnology Solutions for Improved Environmental, Economic and Social Sustainability in Pollution Control. Undoubtedly, we are really optimistic with our future results. We are the coordinators of this project. It's a project where participate 70 partners from 10 different countries, and it's, on the contrary of some of the projects that have been presented here, it's a young project. We bought more or less on 1st of September of the past year, so we have no results for show you. I will show you the intentions of the project. We will finish more or less on August of 26. The partners that take part in this project are free from Basque Country, from Spain. What is that? The University of Basque Country, Ranke, and one company, Iragas. Then we have a partner from Sweden, KTH, and then some of them from Austria, Alchemia Nova, APAR, and Stalhesi. We have partners too from Poland, from Belgium, Renovate and Evolve, from Netherlands, Stage 4, from Cyprus, Atlantis, from Italy, the University of, of Bologna. No, of Bologna, yes. It's the H, don't worry. The Instituto di Ricerca Suacali in the north of Milan, and then we have some special partners because we have a lot of problems with them, not with them, with the Commission, because these partners were out of the Commission. These partners come from the United Kingdom, from London, at the University of Brunel and Times 21, and then we have another part for the United States, the State University of California in Fresno. So we are a really multidisciplinary example of collaboration. The challenge is quite known. You know that the presence of pollutants in our environment suppose a serious threat to human. Being environment pollution a major factor in the decline of the biodiversity? Well, the SynBioRem project, as other projects, as your projects, and probably as new project that will found in next course of the European Communion, but we'll try to propose solutions from remove the harmful pollution from the environmental, obviously using innovative nature-based solutions. In our case, in a more specific way, the main objectives of the project implying the development of 12 different innovative bioremediation solutions, alone or in combination, we will see, able to remove pollution from all the possibilities that we have in the earth. We will try to remove soils, surface water, groundwater sediments, even seawater and marine sediments. And for this, we propose some possibilities. So, we will try, in the case of soils, in the case of soils, we will try to tailor microbiomes and cell augmentation. We will design biopolymers in order to encapsulate different chemicals or things, I don't know what's the name, I'm chemist, don't forget. Cells, enzymes, and this kind of things useful for fighting against the pollution. We will try to the use of gene biomutation based on synthetic auxotrophic bacteria, the bacteria that we have in the polluted sites. We will develop active water absorption geocomposites systems using for them fungi and yeast. We will do some studies in the possibility of the use of bioelectrification for enhancing biostabilization of soils in this particular case, in the case of sites polluted with pH. And finally, the phytomanagement of saline coil and rainwater will be used in some special places that we have in Austria and in the United States. In the case of surface water and groundwater and sediments, mainly we will try to design and use floating islands with immersive tissue surfaces, and in some cases, even we will use animals, freshwater mussels in this case. For seawater and marine sediments, we will use a more chemical way to try to remediate the pollutants using cascade bioreactors for ex situ bioremediation. And at the same time, we will try to recover some methods or chemical substances that we believe that are interesting from the economical point of view. Specifically, we will try to obtain phosphor from the sediments, from the marine sediments, and some methods. And finally, we'll try to combine all these techniques for obtaining cross-cutting solutions in order to provide or to to obtain better guides for the selection of the most adequate technologies and processes from this point of view, from the point of view of the circularity, and we will try to better the risk assessment methodology that we have today in order to introduce this point of view, the bioremediation point of view. For that, and this is the most difficult part of the project, we have got different sites for working. In this slide, I show you the different sites in Europe and in United States, and I have classified the different sites with colors that are related with the kind of site that we have and the kind of pollution that we have. We will work in some industrial brownfields, two in Spain, another one in Brooklyn in Poland, and another one in Schwach in Austria. Then we have the possibility to work in mixed soil waste landfills. We have one example here in Spain. Then we will work in urban diffuse pollution of surface water bodies, and for this we will use a lake here in Austria, and then we will work in some places of the Thames River in London. We will work in agricultural drainage places in Austria too, in the lake of Mersey. We have a really big problem with this problem in this lake, and then we will work in the Central Valley in California, and finally we will work with the water and the marine sediments in Baltic Sea, close to West Stockholm. So the final aim of the project obviously will be the developing of innovative strategies to remove pollution from these all places or from these all sites. Obviously trying to increase the use of the bioremediation. We will develop new circular business models trying to take economical advantage from the remediation activity. We will try to increase the safety of remediation too. And finally, we would like to engage citizens in the increasing of the acceptance of these kind of solutions that, as you know perfectly, are used really in few occasions in the society nowadays. The expected outcomes of the facts and figures that we hope to get when we finish the project will be this all, but I would like to underline some of them. We will try to obtain or to develop 12 new and improved remediation techniques or strategies. We hope to get 20 economical acceptable products from these activities of remediation, and well, we will validate these techniques in at least 8 different places, which for us was quite difficult to get. Then we have another freedom fund, more related with the specific numbers of the contaminants and so on. So this is all. Thank you very much for your kind attention. Thank you for the opportunity to share this project. This is the contact, the official contact of the project. You have the usual places in internet, LinkedIn, and these kind of things. And that's all. It has been a pleasure. Thank you very much.
Hi, thank you very much for the talk. You mentioned citizen participation.
Sorry?
Citizen participation.
Yeah.
I was wondering how that is accomplished, like in what kind of way?
Yes, I don't remember all the stakeholders that we have, but some of them are ecologist group from all of Europe. Here we have specifically Ecologistas Marchan. Okay, yes. And then we have some town halls, some municipios, well, We have some organizations in this case. Yeah.
Eskerrik asko, Jose Luis.
Eskerrik asko, Manu.
Just a couple of very quick questions. Well, I know that you haven't started already with the project, but how many tons of sediment are you expecting to treat with
How many?
Tons. I mean,
Yeah.
That's the complexity, because you are going to do the ex situ extraction of pollutants.
We are working with samples of 20 tons. I say we, the people from Basque Country. The rest of people I don't know, but I believe that in Austria more or less the size of the samples with 20 tons, and in the case of sediments I'm not sure, but I believe that will be a really small quantity of kilograms, because the work in this kind of bioreactors require of small bioreactors. That's the problem. But in the rest of cases, the sample will be quite big. Industrial samples, more or less.
And the second curiosity is, why did you select the Baltic Sea?
The
Baltic Sea.
Because we are working with KTH that is in Stockholm, so they select that. It's a group that is working with the sediments in the Baltic Sea and the water in the Baltic Sea.
But you know that the Baltic Sea is very low salinity level.
Yeah.
And this point is 2.5 PCUs.
Yeah, but I'm not expert on that. They decide to do that. We have this and then some lakes. It's quite strange. I believe that the salt water is a problem for chemists. Yeah, you know that.
Yeah, no, the matrix effect.
Yeah.
Okay, thank you. I'm willing to see your results.
Okay, thank you. We will show you. You're welcome.
Okay, so we are about to end with the last and youngest section of the day, which would be the presentation of 6 of the posters that were presented to the Congress. You know, there are 13 posters displayed, and we selected 6. So I would please ask all the presenters now to keep it faster, if you don't mind, to please sit by order here in the front row. So we will start with Lourdes Epelde, then Iyal Grossman. Please come and sit in the front. Marin Cecile Afholder, then Alejandra Perez, Ana Sofia Sousa, and Sandra Curiel. I would ask you two to present yourselves. Give just the first name and place where you work. And after that, we will have the closure, and we also voted for the best of your posters, so there will be an award for that. So, Lourdes Pelde, you can introduce yourself and present.
Thank you. Okay, so I'm Lourdes from Neger. I'm a soil microbial ecologist, and I'm really happy to be here because I'm in the student section. And and because this study also takes advantage of one of the treasures that you have seen today, which is the network of long-term phytomanagement experiments that has this PHY2SUDOE group. So I don't have to tell you by this time of the conference that phytomanagement aims to obtain more benefits rather than just reducing the risk of pollution. And among those benefits, among the environmental ones, lies the improvement of soil biodiversity. So I have asked this, nowadays, these days they are getting famous, these AI portals. I have asked this DALI AI portal to draw what is soil biodiversity for her or for him. And this is what comes out of it, which looks quite nice in my opinion. But for me, biodiversity, soil biodiversity is much more. Soil biodiversity means remediation. Soil biodiversity means erosion control, water purification, the opportunity to look for new antibiotics, plant production, and many other things. That's why we deal with it, even in these polluted and phytomanaged sites. And the approach we are using in this study to study soil biodiversity and try to shed some light in the complex trophic food web that we have in soils is to use a multi-targeted amplicon sequencing approach to study bacteria and archaea, but also fungi, protista, and the metazoa. And we don't focus only on the structural approach, so not only on who is there, but also on what are they doing, on the functional component of this trophic web. And as I told you, we have been collaborating with all our friends from the PHY2SUDOE networks, and we have sampled 5 long-term phytomanagement experiments where they were all using poplar trees as a phytomanagement treatment. Sorry. And as expected, at first, we saw that the site characteristic or the soil type of each different case study was influencing in a great extent the microbial composition of our soils. So you can see that, for example, the sand content is really higher in Touro, which is the site that Angeles has explained that as before, and also, well, the contaminants are different in each site, so this has a major influence in the microbial composition. We expected that. But if we remove the effect of all those physicochemical properties, contaminant concentrations, and so on, and we try to see the pure effect of the phytomanagement treatment, we can see that there is a small but significant effect of the presence of the poplar trees in this microbial and biological, because we are also looking at other not microbials but fauna in the soil. So there is this effect. And what we are doing now is to try to see exactly which taxa are different between these two treatments, and to have a look not only at the diversity in terms of who is there and what's the relative abundance of each organism, but as I told you before, to try to reconstruct this trophic web and their interactions and try to see what phytomanagement is helping or not in this matter. So I don't know if you have questions, but I do have some. So, for example, the first thing that comes to my mind, and taking advantage that many of you are included in this study, I would like to discuss with you later, that in terms of biodiversity improvement, we have seen that there is a change, but maybe not so big. So is phytomanagement required, or in this case, just the spontaneous revegetation that is happening in the control plots is enough for improving soil biodiversity, or for this happening a long time? Or is this a sampling bias that we are introducing because we are just studying the surface of the soil, the first 10 centimeters of the soil? Or I would like to try to study in temporal terms the results that we are having here, because we have seen that they are all more or less long-term experimental sites, but some of them are 5 years old. There are others that are 10 years old. There are others that are 15 years old. So maybe we could try to see a long time if the complexity of the microbial also faunal networks are getting recovered or not with time. So yeah, these kind of things I would like to discuss with you later on. Thank you.
How good do you think is the prediction of functionality, at least in the past, to be able to link structure and function, you were supposed to cultivate the microorganism to
Yep.
study functionality. Most of them are not cultivable. How good do you think is that prediction of functionality?
I think it's getting much, much better because we know more and more the relationship between function and structure. And even if it's criticized because yeah, we are using an amplicon sequencing approach and we are not studying functional genes in themselves. And what these systems use is a phylogenetic relatedness among organisms with known function and the ones we have found in our soil. So this is limiting, I think. But we have seen that maybe using this approach can be even more powerful than using metagenomics. Yeah, because with this approach, as it's getting cheaper and cheaper, you can afford to do many, many samples. And in metagenomics, we are still being very careful and doing few samples. And I have seen studies using both approaches that they obtain better predictions in the metabarcoding approach than in the metagenomics approach. So I think it's going good.
Okay. So hello everyone. My name is Eyal Grossman. I'm a student at Porter School of Environmental Studies at Tel Aviv University. And first of all, thank you for giving me this platform. It's a great honor to be here and to meet all of you. And it's very inspiring, the amount of work done in Europe. We need more in the Middle East and more in Israel for sure. So today I will present my research. I'm a PhD student, I said. This is the research for my master's. It was done 2-3 years ago. It's called Simulated Herbivory Enhances Cadmium Phytoextraction Efficiency of Sunflowers. Back in the days, I really wanted to speed up the process of metal extraction. Since, as was mentioned here today and maybe yesterday, from the human perspective, time is a very important factor, so I wanted to speed it up. So traditionally, at least in the literature, there were two approaches of speeding up heavy metal uptake. One was by increasing metal bioavailability with the compost or EDTA chelators, and genetic engineering with focus. No, sorry, what did I do? Focusing on specific traits that we want to promote. But with these two approaches, there are some limitations, such as the risk of harming nearby organisms and unknown impacts on the ecosystem. Interestingly, the ecological drivers for metal hyperaccumulation are rarely considered, at least in the literature. So why do plants accumulate heavy metals, and specifically non-essential heavy metals? And the prevailing hypothesis until now is called the elemental defense hypothesis, that posits that plants use toxic heavy metals as a defense strategy against herbivores. The idea is that the metals are in the ground, and using them is cheaper than producing organic compounds. Also, plants can accumulate multiple metals that can give them defense against multiple enemies. And there's also correlation between the feeding sites of herbivores and where the metal is accumulated. So we ask, can herbivory induce heavy metal uptake? And what we did, we chose the Helianthus anus because it's beautiful and it's a very strong plant. We chose cadmium as the studied metal, and we didn't use real herbivores because that's very hard to control. We used simulated herbivory by jasmonic acid, which is a phytohormone that does many things, but it's heavily involved in defense mechanisms. And we did 4 different treatments. So one with, one group with 5 milligrams of cadmium per 1 kg of soil. And we did the control solution and a simulated herbivore. And the other one we did with the 10 milligrams of cadmium per 1 kg of soil. And we chose these levels because these represents below and above the cadmium threshold regulations in Israel. What did we find? Basically, we found many things, but in this presentation, I'm only showing the concentration levels. So we can see that the cadmium increase in the soil was a significant factor with elevating cadmium uptake. And by the way, this is only the leaves. In this study, we checked only the leaves. That was, from the ecological point of view, that was what's important. But the amazing thing is that the jasmonic acid, the simulated herbivory treatment, increased it both in the low metal and the high metal by significant percentages. So, can herbivory induce metal uptake? Yes. We found that specifically in sunflowers, we saw induced cadmium accumulation, and this also points to the evolutionary history of sunflower or this Helianthus species, the evolutionary history of that and cadmium. We saw that the elemental defense can be a facultative trait. It used to be thought that hyperaccumulation is a constitutive trait, but here we can see that we can induce that. And we think that simulated herbivory using jasmonic acid spray can provide a risk-free tool for phytoremediation operations and optimization without the need of sophisticated machinery. You just put the jasmonic acid in a spray container and you spray it. And that's it. Thank you very much. Okay, good, I think.
Okay, thanks a lot. Which ones are the disadvantages of using jasmonic acid? Because you have said that it's well, I'm not a plant physiologist, but you have said that it's a molecule involved in many different things. Maybe you are affecting one thing positively and another thing negatively.
So you can see also in the poster, in the poster I show it, and also in the paper, you get lower biomass. And from a production point of view, maybe this is bad, but this goal was not to produce yield, was to just increase the uptake. And although I showed the concentration here, and this could be, how do you call it, a reflection of reduced biomass, but the total uptake, which means the concentration and the biomass, is still 40% higher. So we need to do more experiments about how, let's say, spraying jasmonic acid will affect the local plant community. But from what I read in the literature, I can't see any harmful effects.
Thanks. You opened a very large debate. I will try. No, I will be short. Remember the work of Elizabeth Pilon-Smith? She demonstrates that the caterpillar and the moth, they adapt to, the population, they adapt to the exposure.
Yeah.
And finally, they bypass this defense system sometimes. Not all, but some. We did it with some caterpillar and alfalfa with contaminated soil, and we did not see any effect. And the third point is, if I remember well your poster, you have a decrease of the biomass of the plant when you spray with jasmonic acid. Yes?
Yes.
So when you multiply the concentration of cadmium by the biomass, in fact, the phytoextraction is decreasing.
No, you can see over there.
Or it is more or less the same. Because what is important is not only the concentration in the leaf, it is also the biomass, because what you phytoextract, it is when you multiply the concentration by the biomass. And finally, maybe it's because you have less biomass, so less dilution in the biomass.
Yeah, that's what
you have an increase.
That's what I mentioned, and I show over there in the poster also the total not the concentration, but the total uptake of the metal that is still higher.
Okay.
Now, regarding the remark about the herbivore repellent, this was the master's. Now in the PhD, I am doing similar experiments. I'm also dividing some methods there. But we did check the effect on Prodenia. I don't know the Latin name of this, but it's a caterpillar, a generalist caterpillar. And we saw that the concentrations of metals does not repel it at all. It doesn't care about the metal. But once we spray the jasmonic acid, it does repel it. And we think that there's another thing happening. So maybe and this still needs analysis, maybe the sunflower also uptake a lot of heavy metals, or the cadmium, and also produces organic compounds to repel. So you get both benefits from the spraying with the jasmonic acid.
It's just a comment. Well, in this case, jasmonic acid is a phytohormone. Is part of the induced system response of plants, not only to herbivores, but also to all pathogens.
And metals.
So part of the reduction in the biomass could be because plants are inducing response, I mean in the wall, cell, and producing phytoalexins, so compounds just to kill microbes in general. So in one way, you are maybe that plants are healthier in some way because it's it's the hormone the plants use just to defend themselves from herbivores or other pests. But that have a cost. Maybe the biomass is reduced because of that, but maybe you get something because the plants could be healthier in some way. They are protecting themselves, I believe.
By the way, we grew it until the first stages of the flower development, and the ones with the jasmonic acid had smaller flowers. So the reduced biomass is a product of the reduced flower, but it wasn't the stem or leaves biomass. Maybe the roots, but we didn't check the roots.
I don't see the point because related with the concentration. I don't see the point why this phytohormone could increase the concentration in the tissue. Well, maybe the carbon derivation to flower or whatever could have some, or maybe the transpiration. I don't know.
Okay, thank you very much.
Hello, so I'm Marie-Cécile Folder. I'm a postdoctoral researcher, so I'm neither a student nor young, but thank you for letting me presenting anyway. So I'm going to present some of the results from the PHY2SUDOE project, which is about the phytomanagement of dieldrin in historically contaminated agricultural soils. I need to be, okay, sorry. So this project started in 2001, and I'm going to present some of the first results we got from the first experiments. So I don't know if you all know, but dieldrin is an organochlorine pesticide like DDT. It was widely used in the 50s and the 70s as an insecticide. But the problem is that it's toxic and persistent. This is why it was banned in France in the 70s for agricultural purposes. But even 50 years later, on plots that were cultivated all the time, this molecule is still present in arable soils. So although it's very hydrophobic, it can still be taken up by some plants, and particularly from plants from the Cucurbitaceae family. And the problem is that in some cases, concentration in the fruits, so cucumber, zucchinis, can be over the maximal residue limits from the EU regulation, so the farmer cannot sell their production. So we needed to find some phytomanagement solution to minimize the transfer to the food chain. So we identified two axes to achieve this goal. which was the first one was to find some like short-term solution for the farmers by decreasing the contamination in agricultural products. So for that, we wanted to identify cucurbitaceae species or varieties with low concentration in the fruits. And the second way was to basically do phytomanagement to reduce the contamination in the soil, like the available contamination in the soil. So we wanted to identify high accumulating plant species amongst cucurbitaceae and also maybe non-cucurbitaceae. So the first year we did a huge screening of cucurbitaceae species and varieties. So we tested 28 varieties from 8 species of cucurbitaceae. And for the phytomanagement, we were screening like 24 species amongst 14 botanical families. So we cultivated all those plants in pots in situ, filled with historically contaminated soil, as you can see on the pictures. So now about the results. So for the contamination management in agricultural products, so you can see here the concentration of dieldrin in the fruits for all the varieties we tested for the different species. So you have zucchini, cucumber, pumpkin, and watermelon. So we can see that amongst the different species, cucumber was the one that was accumulating the more dieldrin. And we identified 2 species, which is bitter melon and watermelon, which accumulated very low concentration in the fruit. The thing with those species is that we tested only one variety, so we don't know if it's a characteristic from the species or if we were very lucky and we just selected varieties with very low concentration. Concerning the effect of the varieties, so we see only like intraspecific differences for cucurbita pepo, so it's zucchini, probably because it's also the species for which we tested the most varieties, so we tested 11 varieties for cucurbita pepo. And we could identify a few varieties with low concentration in the fruits, so the Noir Maraîchère, for instance, the Mirza, and the Copana. So varietal selection for this management of contamination in agricultural products can be quite a good solution. So more tests needs to be done on other species, but now for the phytomanagement of contaminated soil, you have here the total dieldrin extracted, so for cucurbita pepo, all the varieties we tested, but also for the different species we tested. So in green, it's the dieldrin extracted in the leaves, in brown, in the roots, and the red is the percentage of dieldrin extracted from the pot, so the total. So we can clearly see that cucurbita pepo is the best extractor, whatever for all the varieties, even the ones that accumulated not much in the fruits, so Mirza, for instance, and Noir Maraîchère. And they mainly accumulate in the aerial parts compared to the other species. So the other species, they mainly don't accumulate much, except vetiver, but most of the dieldrin stays in the roots. So yeah, to conclude, so we could identify some zucchini varieties with low concentration in the fruits, which is interesting. But even those varieties with low concentration in the fruits, they are able to extract an important amount of dieldrin in the aerial parts. So we could have up to 10% of the dieldrin extractable in the soil that goes into the plant. The vetiver was the only non-cucurbitaceae species that was able to extract dieldrin, and by choosing the right cucurbita pepo varieties, we could actually achieve both of the aim with producing low concentration fruits with low concentration of dieldrin, but with high accumulation in the shoots. So it's interesting both for contamination management and for phytoextraction. And thank you very much. Questions? Thank you. Good afternoon. My name is Alejandra, and I'm going to present the poster titled Assessment of In situ bioremediation and phytomanagement strategies in soils with amended with sewage sludges. Well, anthropogenic factors such as industrial growth, among others, degrade the soils by the increasing of landfills and waste disposals. According to the Basque Country regulation, there are a total of 1,277 landfills, including the landfill 17 that is located in Guernica-Lumo. These soils are amended with sewage sludges from a wastewater treatment plant. And these soils were treated with a combination of bioremediation and phytomanagement strategies involving micro, vermi, and phyto technologies. Well, the aim of the study was to assess the application of the combination of these strategies. Well, the methodology was carried out, like, firstly, with the preparation of the area in order to apply all the combination of the different biological techniques. And this was applied in all the plots except the MN8, as Chema explained it before. And after this, we collect soil and the vegetation cover of the plots in order to do a chemical analysis of both, and also to calculate the diversity and biomass of the plants. Also, we did different toxicity bioassays. First, the root elongation test with Cucumis sativus, then filter paper test and soil test for earthworms with Eisenia fetida, and different microbial parameters as respiration activity and Shannon diversity. And the earthworms collected from the soil test were, like, in those earthworms, a cell viability analysis and riboflavin contain analysis were carried out. And then with the results, we can see that in the soil chemical analysis, we calculate the percentage of elimination between the 21 and 22 results. And we see that in all the compounds decrease, but it's remarkable how tile drain decrease. And we also can say, like, in the filter paper test, and the soil test, it's shown how with a longer exposure the biomass decrease. And in the Gaussian fluorescence, we can see that the MN8 plot have a lower soil homocyte viability. And for the plants results, we can see that the plant biomass and the diversity is related with the levels of pollutions. And the point MN8 show lower plant biomass and a higher plant diversity. So we can say that the pollution levels were higher. Also, with the extraction of the metals results, we see that it's present, like, in the highest level is in the MN1 point, but we need to take in account that this point have the presence of Salix atrocinerea. And also, as conclusions, we can see that the Salix atrocinerea have an influence in the metal extraction from the MN1 plot, as this species is a highly
hyperaccumulative species, especially for the cadmium. Also, with the toxicity assays of the plants and earthworms, we can say that the worst quality and health of the soils is in the MN8 plot. And in the microbial parameters, there was not remarkable difference between the groups. And as a general conclusion, we can say that this combination of technologies that were assessed helps to eliminate the contaminants and improve the soil health and functionality. Thank you very much.
Sorry to monopolize the microphone. You're puzzling me about the dieldrin. It's so exciting to see that the dieldrin is disappearing, but I'm balancing between two things. Do we have really some reaction of metabolization of the dieldrin and really a dissipation, I mean biodegradation? Or, because I know from the work of Marie-Cécile, that in fact we extract the dieldrin with a solvent. If after the transfer in the gut of the earthworm, for example, the dieldrin become more link, more store or link bond, not really bond, associated with the turricule of the earthworm, and that the dieldrin is becoming not extracted by the heptane. So are we sure that there is really a dissipation, I mean a degradation of the dieldrin, or is the dieldrin much more unified in the turricule, I mean the feces, for those that are not aware about earthworms, they are producing feces, and the dieldrin can be even more sold to the organic matter produced in the feces of the earthworm. So that's a question. I have not the answer, but just to open your mind about this.
I do not have the answer also.
So it's a big problem, really the dissipation. Do we have really?
Thank you. Like, I don't have the answer.
If you have biodegraded the dieldrin, congratulations, you will win the award in any scientific society. It shows that you cannot imagine how it is relevant.
Yeah.
You know, when we try to extract the dieldrin, we are doing before the treatment and after the treatment. So all the process you are talking about should be there anyway. And from your data, the data of Marie, I see that the level of dieldrin absorbed by plants is really low. No. Yeah, is 1,000 ppms. Yeah, is micrograms by kilo of, is micrograms, not milligrams, micrograms by kilo of fruit. Yeah. Just take 1 0 only. Is 10,000 ppms. No, it's, well, it's, let's say, 10 micrograms per kilo of dry weight. So it's really small, it's a very small amount, and we are, in these soils, is about 30 ppms of dieldrin we found. And we extract ppms, yeah. And then, and we extract that, and after the remediation, it appears 0. So you are extracting in the same way, even if the process you mean that we should consider anyway.
One idea could be to cultivate cucurbits before and after the vermin remediation. I did the test according to what you present. Last year, we tried. The cucurbits were growing better in the presence of earthworm. There is an
Okay, so hello everyone. My name is Ana Sofia Souza, and I'm an early career stage microbiologist. I finished my master's degree in 2021, and since then that I've been working in PHY2SUDOE project, directly and proudly in Helena Moreira and Sofia Pereira's team in UCP. And I want to thank the opportunity to present my work here today, our work. And I'm going to talk in a very short version of one of our works, that is the inoculation of rhizobacteria isolated from the soil of mine tailings, and its potential application as biotechnological tools to foster plant growth. So, as we all know, and have been talking about during these days, soil contamination is a problem, a worldwide problem, and the main sources of this contamination can be due to anthropogenic activities, such as mining activities. In this case, you are talking about mine tailings that can have gather several problems to the soil, and the characteristics of this soil are low organic matter content, a very acidic pH, and high metal concentration that leads to a poor vegetation cover and the risk of surrounding areas contamination. So that is where the phytotechnologies enters in action. There are plant-based approaches used to degrade or immobilize these contaminants. In this case, I'm going to talk about the bioaugmentation, so the use of beneficial microorganisms that can help the plant to grow, and they can also help in the degradation of the contaminants in the soil. So, the main two goals of our work here was the isolation of metal-tolerant rhizobacteria from the most abundant metallophytes that we found on Borralhas mine tailings, and also the characterization of their plant growth-promoting traits. So, for the bacterial isolation, we collect soil from the rhizosphere of the most abundant metallophytes that we found on Borralhas mine tailing. We made a composite soil sample. And for the bacterial isolation, we added to the soil an enriched metal solution that comprised cadmium, copper, lead, and zinc. And the most tolerant ones, that were 37, we identified them. Then we characterize them in terms of their PGPTs that can help, that are characteristics that can help the plant to grow and to uptake nutrients. Here are 4 of those PGPTs that we tested: the indoleacetic acid production, siderophore production, solubilization of phosphorus, and biofilm production. And we found out that we had a lot of growth-promoting traits in the bacteria that we isolated from the mine tailings. After some biocompatibility tests between these 37 isolates, we found out that most of them showed antagonistic behaviors. So to apply in a greenhouse trial, we chose just one bacteria, Bacillus villanoensis, that gathered the most positive characteristics and is also a fast growth bacteria. For a short-term greenhouse trial to test the potential, the biotechnological potential of this bacteria, we used Agrostis stolonifera, fast growth bent grass, and Borralhas mine tailing soil. Then we applied, we had 4 test conditions. We applied 10% of compost to the soil, and then with the compost we had our bacteria and also a mixture of the bacteria and herboscular mycorrhizal fungi spores. Then, after 4 weeks of the inoculation, we evaluated the plant growth of the plant, and we found out that with the addition of the vermicompost, we increased the height of the plant and also the shoot and root dry weight. And also with the application of our bacteria, we increased even more these plant characteristics. Then we also evaluated the microbial activity of the soil, and we found out we corroborate the plant growth results, since with the vermicompost addition and also the bioaugmentation with the Bacillus villonensis, we increased the microbial activity of the soil. Therefore, we can conclude that the rhizospheric soil of the mine tailings harbors a lot of interesting microorganisms, since most of them showed plant growth promoting traits, and also the addition of vermicompost and the bioaugmentation with the bacteria increased, in fact, the plant growth and the activity of the soil. Thank you so much for your attention, and if you have any questions, please. Okay. Thank you so much.
Hello, my name is Sandra Curiel. I'm from University of Burgos. I work with the composting group of University of Burgos and with the ICRAM Research Center that is also in Burgos. And first of all, I'm not going to talk about phytoremediation. So yeah, it's a bit different, but we have a high concentration, very high concentration of total petroleum hydrocarbons. So we start with other bioremediation technologies, and then we can continue with phytoremediation. So if you need to know more about this, let's talk with my colleagues, because they are working with phytoremediation. So, okay, yeah. Why it's important in this study? First of all, we need to have some background information. We are overusing energies. We are overusing hydrocarbons. So we have now some risks. We are taking some risks. We have risks in human and ecosystem health because of this contamination of hydrocarbons. So we are working with bioremediation. We are working by biostimulating soils and by bioaugmentation of soils, and we are testing some methods, different technologies, using different organic amendments by adding consortia, microbial consortia, because we have very high concentration of these recalcitrant hydrocarbons and also heavy metals. So how are we working on it? We are working on lab scale, on 90 days of incubation of soils, of 200 grams of soils. So we prepare different mixers of them. We add vermicompost, different type of biochars, rhamnolipids, and we are used to add to improve the capacity of the microbial consortia. We are trying to add consortia and microbial consortia previously isolated from the soil under study. So we are doing different sampling points, and we are making analysis of TPH, physicochemical analysis, microbiological analysis, and then we have really good results. In this concentration, we have really good results. You can see here that we work between 5,000 of ppms of total petroleum hydrocarbons. So now, when we prove and when we analyze these treatments, we can have we have a significant difference between controls and treatments, between controls and biostimulation and bioaugmentation. The better controls has been in the bioaugmentation with vermicompost, but we have a problem here. As you can see here in the chromatographs, sorry for the scale because it's different, but you can see here that in the short chain hydrocarbons, we degrade it at all. But here in the circle one, in the ones that are the long chain hydrocarbons, it remains here. It goes down, but it remains here. So what is the problem? What is the conclusion of our work? We have good results with bioaugmentation. You are working with lower concentration of hydrocarbons. We have good results, really good results, but we need to solve the problem of the long chain hydrocarbons. So it remains there. We are working with all soils. We are working without volatile fractions. So as you can see, we eliminate the large fraction, but some stays there. So this is because of the recalcitrant part. This part is low viability, so what are we doing now? What can we do? Now we are continuing with the work, and we are working in different scales. We are working in microcosm scale, trying to improve this viability of the recalcitrant part by adding biosurfactants inside the soil. We hope to have good results. We are just starting with this experiment. Then we were working with pilot scale, and here we have really, really good results because we were working with this concentration of hydrocarbons with 34,000 ppm of total hydrocarbons, and now, well, not now, at 90 days we have 3,300 ppm, so really good results, but the recalcitrant part stays there. So now we are working in a real scale with biopiles, and we are trying to add a new synthetic community, microbial community, not the one that we isolate from the studied soil. It's a community that degrades hydrocarbons, so we try to put it together with biosurfactants, with nutrient solution, with the best amendment that we have, and we are trying to solve this recalcitrant problem. So yeah, that's all. We hope to have good results.
Really interesting. Are you in touch? It's an idea I pass you. Are you in touch with Professor Morillo in Madrid? She is especially using cyclodextrin to increase the solubility of the recalcitrant POPs. I did it myself. It's a problem when we had, less than 1% of cyclodextrin. It costs nothing, beta-cyclodextrin. And in fact, it's making a cage where it is hydrophobic in the inside and hydrophilic in the outside. So you can increase the solubility of some POPs, and especially hydrophobic POPs like you have.
Yeah.
But don't add too much. I was testing 0.5, 1%, 3%. 3% it's too much because the soil became hydrophobic, and after that we have problem with the development of the plant. But be in touch with her. She's working in Madrid. She's an expert about that. And you can test especially additional rate less than or around 1% or less than 1%.
Yeah. Okay, thank you. I was working in the Josef Stefan Institute in Slovenia, in Ljubljana, and there they are. They know a lot about colloid biology, and we are trying there to add carriers with some hydrophobic and hydrophilic part to try to increase this degradation of the recalcitrant part. They are working now on it. Yeah, thank you.
Okay, thank you everyone for staying so long. We have to close the event, and I would like to thank all the partners and the people that came today and yesterday to this conference. I'm really glad. I'm afraid we are a little bit late on time as always, but we try to keep it the best we can. So thank you so much, and I hope we will see you in the future in maybe another cooperation projects. Now Carlos will give the award for the best student poster.
Okay.
And this is the...
Okay, it's like in the Oscars, you know. I want to thank my mother who always supported me. Okay, the best poster goes to Alejandra Perez for the assessment of in situ bioremediation and phytomanagement strategies. Congratulations. Maybe we can take a picture. And now, well, during the coffee break, Juan has asked me to close the event, and the PHY2SUDOE. To close the event is very easy. Just to say thanks a lot to the organizers, to Thea, to Juan. It has been a fantastic event. Unfortunately, I couldn't be here yesterday, but the list of speakers was impressive. Second, to thank all the speakers for very stimulating, talks. And of course, third, to thank the audience for being here. I hope you have enjoyed the event. Congratulations, Juan. I think it has been great. And then he has also asked me to close the PHY2SUDOE project, which I'm not going to do, because I do believe and I do hope this is just a pause, a break. And I do hope that this year we will be able to look for funds to continue working together. I'm positive, we can get the funds to find the right call, because the most important deliverable of our project is that we started as a network of collaborators in 2016, and we have ended up being a network of friends that collaborate. And that, in my humble opinion, is the most important deliverable. So since I don't want to get emotional, I'm going to close the session, and I'm not sure if we are going for lunch. If I have a couple of drinks, I will cry, and Carmela will tell me, you're a softie, you're a softie. Thank you so much, everybody, PHY2SUDOE friends and everybody. Thank you so much.
Just a logistic last note. We have to take out the posters, so if you want to take them with you, just take it out. And remember that this has been recorded, so anyone that missed one presentation or wants to go back to anything, the slides and the presentations will be on the website. So thank you.